Good morning, sir.
Morning.
Yeah. Sir, we are having 55 participants joined. So should we wait for a few more minutes, sir, or should we start, sir?
Yeah, we can start. Yeah, we can wait for another 2 minutes.
Okay. Okay. Sure, sir. Sure. Okay. Thank you, sir.
Firoza, could you send that document yesterday?
Sir, I have forwarded the document to Gaurav, sir, for forwarding the same to Dean ISI.
Okay, so you incorporated the corrections I suggested, no?
Yes, sir. Yes, sir. Yes, sir. All the corrections, sir.
But Gaurav has not sent anything yet. Can you give him a reminder?
Okay. Sure. I will do that, sir, right now. Thank
You
you,
tell
sir.
me when to start.
So we can start now because people are joining, like the participant count is increasing. So we can start, sir.
Okay. Okay, let me share my slide and then
Okay, sure, sir. Sure.
we'll start.
Good morning, sir.
Good morning, Shubhasachi.
Shubhachi. Sir, the presentations have been very beneficial, sir, up to now. Mainly the career recovery and that synchronization part, sir. Thank you so much for the session.
Thank you. Thank you.
Hope to learn more. Thank you. Thank you, sir.
I'm going to present today something which is very, very vast. Is my screen visible?
Yes, sir. Visible
Yes,
to me.
sir.
Yeah.
Yes, sir. Yeah. So can we start, sir?
Yeah.
Yeah. So a very good morning to all the dear participants, experts, and our coordinators. So today we are going to start with the day 4 session. So I would invite Professor Ratnajit Bhattacharjee, sir, to please start the first session of day 4. Thank you, sir.
Thank you. I hope I got some feedback from Sabbosachi that the sessions are progressing well. So this is the main objective of conducting this type of FDPs, where we share a platform, we share our views, learn from each other. I hope today's all the three today will be well participated and people will raise questions and we'll be able to discuss. So today I'm going to discuss only the basics about the channel coding, block and convolution codes. If you remember the very opening session, I showed the block diagram of the communication system where we had source coding encoders and then the channel encoder, and on the receiver side we had the decoder, channel as well as for the source codes. Now philosophically the source code, they try to uh, remove any redundancy that is present in the information, rather try to compress or make the information stream shorter. Whereas in channel, as we have seen so far, we encounter various types of disturbances, particularly the most prevalent one is the Gaussian noise, and most of the systems are actually designed to in Gaussian noise. And then we have seen that wireless system, when it comes, we need to take into account the fading scenarios as well. The channel coding, the philosophy is different. Here you add redundancy. Here in the source coding we are removing redundancy. In the channel coding we add redundancy. The number of bits generated by the source, the number of bits actually goes into the channel is more than that. Now, why this redundancy, how it helps? So it helps to actually reduce the error that is introduced by the fluctuations in the channel. And of this was laid once again Shannon's theorem, fundamental on information theory. So he said that given a discrete memoryless channel, in that sense, the symbol is perturbed by the noise independently of the other symbol. So when you are transmitting a stream of symbols, the uh, perturbation that is produced in a symbol is not symbols, but it is by the noise. A capacity C and the source with a positive rate R less than C, there exists a code that output of the source can be transmitted over the channel with arbitrary small probability of error. So this was his theorem and gave the formal proof. But this is very important. The capacity of the channel, it is the upper limit of the rate that you can through any channel. And suppose you are generating information at a rate less than C, then there exists a code such that the output of the source can be transmitted over the channel with an small probability of error. Shannon's theorem is essentially error-free transmission in the presence of noise. There is a but or however. The theorem tells about the codes, but does not tell how to construct these codes. So it was left to the later researchers to come up with schemes by which this observation made is exploited practically. And today we have a large number of codes. And in fact, information and coding theory has established itself as a very, very important stream. And we do offer specialized courses on that. So in this 1 hour discussion, I will try to cover only the very basics of this, which are relevant from the point of view of, we should understand the type of errors that are introduced. In some cases, the error that occur, these are isolated errors. Usually, if the channel is noisy, you will find noise is affecting one bit, and then there are some good bits, then there is another, like that. But there are scenarios when a large group of bits, they go into error together. For example, when in a fading scenario, when an outage occurs, so you will find that you are not receiving any bits, and so this type of conditions. That's why the modeling is either the channel changes the bit, so a 0 is made to be decoded as 1, thus making an error. The bit is changed in such a way that a 1 is decoded and the receiver is 0, you make an error. There are some cases when we find eraser, some bits are removed, or the block fading type of scenario where we have a large number of a group of bits are affected together. So all these scenarios, they require special treatment. We will not go into those very details of the scenarios where the error can be handled. We will restrict our discussion only to isolated errors. That means you are transmitting a long stream of bits, out of which one bit may become in error, and then there will be a stream of good bits, then another bit. In this type of scenario, we will try to apply this coding concepts, because as I told, this is very, very involved. We cannot cover everything in detail. So we construct codes. So there are different forms of codes, and as the title slide says, the code may be a block code. That means you will take a block of information bits and then encode. It may be a convolution type of order where you see that we can put the information bit serially. So a code is said to be linear if any two code words can be added in modulo 2 arithmetic. The modulo 2 arithmetic where we disregard the carry. In simple terms, you can say that it is the exclusive of OR operation to produce a third code word in the code. So we are talking now in the context of block codes. So if we have, say, a block of size 4, then we will have the information bit sequences can be 16. Now this block of information bits can be encoded. As I told, redundancy is added, so that means we will add additional bits. It will be mapped to, say, the code length may be 4 plus 3, 7, for example. Now we will have actually 2 to the power 7 possibilities. So out of which only 16 are needed to represent the combination that is produced by our information bit, 16 combination. So you can see that 2 to the power 7 is number. 2 to the power 7 is 128. So out of that you are using only 16, remaining you are not using. Now on what basis you choose this 16? So this is what we are going to discuss. So a code is said to be linear if any two code words added in modulo 2 arithmetic produces a third code word in the same code. So we talk of NK block codes, where there are a source or information bits and n minus k parity bits. So I told about 7/4 code, for example. In a 7/4 code, we have 4 information bits, and we introduced 3 additional bits, which are called parity bits. And we define the code rate R to be equal to k by n. So you can see that code rate will be 1. And what does it mean? We will be transmitting through the channel more number of bits than actually our is producing. And as a result, now if you want to transmit more number of bits, you require and maintain certain rate, you will require, say, higher bandwidth. Now, so the resources, communication resources will be utilized in sending more number of bits. And the advantage the give us is that it should reduce the error. So these are the basis on which the performance of the codes will be evaluated, the complexity in implementation of the coding scheme, what is the code rate it can achieve, what error rate performance improvement it can provide. So based on all these things, the choice of the code, a particular code will be made. So we talk of systematic block codes where the message bits transmitted altered. So out of these n bits, k bits message as it is, and n minus k parity bits are added. Codes can either correct or merely detect errors. So this is important depending on the amount of redundancy contained in the check symbols. So certain codes, they are designed not to correct the bit, but just to detect the presence of an error. For example, in the very simple form, possibly when you configure your communication with your peripherals in your machine, you set the parity, even or odd parity. So one additional bit is added, for example, to the 7-bit code. So you make it 8. Now this can actually detect an error. Now how many errors it can detect, all these things depend upon how much redundancy you can using. So this detection is also sometimes very helpful to us, and there are a host of protocols which have been developed. For example, error detection useful in ARQ, automatic repeat request, which is used in the link layer, data link layer of the uh, communication networks, where you transmit a frame, perform some check on certain fields, and then it comes out that the frame has not been received properly. Then what the receiver has known the the frame has not been received, so you send a feedback. So you need to have a feedback channel through which you need to transmit this information. Frame has not been uh, received. So there are different ways of doing it: positive acknowledgement, next, sometimes in the, if it is a bidirectional link, information is piggybacked. So there are different schemes by which it is implemented. The essence is that you will have to inform the transmitter that the receiver has not received the packet properly, and then you request for a retransmission of it. So there are again several strategies has been developed based on this ARQ protocol and very much used in communication systems. We have selective repeat, we have go back and this type of stop and wait, this type of protocols have been developed, which depends on how efficiently you can detect that there has been transmission error and then request the uh, transmitter to send this information back. But if you this, there are codes which not only can detect but also can correct the errors. Error correction is because it merely says that the frame that I have received is not the one which is transmitted. If you want to correct it, you not only have to detect the error, but also you will have to locate where the error has occurred and then only you can correct it. So this type of strategies are called forward error correction or FEC, and the codes that can correct errors are known as error correcting codes. So we'll see that number of bits you can actually correct in an FEC will depend upon the redundancy that you are using. So let C1 and C2, is my screen visible and voice is audible? Pubali?
Yes, sir.
Screen
Hello?
is visible properly and voice is audible?
Yes, sir. So the screen is visible as well as voice is audible. Yes, it's clear, sir.
Okay, so let C1 and C2 be the two code vectors having the same number of elements. Now we introduce some terminologies which are very much used. So Hamming distance D between this C1 and C2 is the number of locations the respective differ. Once again, you can find it out by modulo 2, or you can do the exclusive or and know that where the two code words they differ. So this is the Hamming distance. Hamming weight WC is the number of non-zero elements in the code vector. In other words, you find out the Hamming distance with respect to a all zero code. So DC1 C2, the Hamming distance is actually weight of C1 C2 added in modulo 2. I think I have used the wrong symbol. It should be, anyway, I'll correct it in the slides later. Minimum symbol, minimum distance, dmin of a linear block code is the smallest Hamming distance between any two pair of codes. And minimum distance of a LBC is the smallest Hamming weight of a non-zero code vector. So either way you can tell, and we'll see that this minimum distance D of a linear block code, it plays a very important role. Yeah, the other symbol here, it is correct. The Hamming distance between S1, if S1 is given as 101, 101, and S2 is 001100. So if you do modulo 2 addition, then you can see 1 0 0 0 1, and therefore the distance D12 is the weight of these, Hamming weight of these, and that is equal to 2, and that means these two code words, they differ only in two positions, and this, for a small code, see it visually. For example, this position they differ, and in these two positions they differ, and this is what you get when you perform modulo 2 addition. To guarantee the detection of up to S error in all cases, minimum Hamming distance in a block code must be dmin is equal to S plus 1. To detect error and the minimum Hamming in a block code must be S+1 if you want to detect up to error. So once again, we express with this example. Suppose our data bits, these are 0001 1011, and we make the corresponding word 000011 101 110. How we make this code word? If you look carefully, you can see that we have added the code word, the bit or additional bit in such a way that we always have even parity. So one odd number of ones, we have made it even number of one. 10, we have another one. Here it is 11 already, 2 bits are 1. So we have not added any 1, we have added 0. So these are the 4 valid code words. Although you can see that with a 3-bit code word, you can actually 8 different combinations. But out of these 8 combinations, we have picked up half of them, 4, which actually has even parity. And these code words are representing our data. Now, if you look at this particular code words, dmin is 2. You take any 2 code, minimum distance is 2. For example, the difference you can see in 2 places. At least in 2 places they are differing. All right. So dmin is 2, and therefore this type of a code can detect one error. Please note that I am talking of detection. So this code guarantees detection only a single error. If the third code word 101 is sent and one error occurs, one error occurring mean it may become 111, it will not match other 3 code word. It may be 001, again it will not match to any of this code word. It will become 100. Just one bit error is occurring if, and it will code word. So if you take this example 101 and the received code and one bit is the 3-bit position is changed, the received code word does not match any of the valid code word. And when you find that what you are receiving is not matching with your valid code word, you know that an error has occurred. And you can detect this scheme that you can detect at least. Please note that here I want to make a comment that when we are transmitting information in form of blocks, a linear block code, we are transmitting information block by block, and the block length is not very large. And when it is isolated errors, it is unlikely that in a block will change. This type of a scheme therefore works well practically when the error in the channel, error produced by the channel is low and it does not affect more than 1 bit in a transmission of block, and the block also usually is kept very not very large. For example, if you are taking ASCII codes and adding 1 bit parity, you are essentially transmitting 8 bit. If two error occurs, may match a valid code word and the errors are not detected. For example, if two errors occur, if this one gets changed to 0 gets changed to 1 and this 1 gets changed to 0, you get a value 110, and in that case it matches your valid code word, so you will accept it as a error free transmission, although whatever was transmitted that has got changed in the channel, but still you are accepting it is a valid transmission and therefore you are committing error. So you can check with 0 0 is transmitted and 2 bits are changed, it becomes again a valid code word. So this particular code can find if this detect error, if this error is restricted to 1 bit. If it is more than 1 bit, it may not be able to detect that error and that erroneous accepted. Now comes the error correction capability. An NK block code of minimum distance d mean can correct up to t errors where t is less than equal to, now this denotes the largest integer less than equal to the enclosed quantity. So it is t is less than equal to largest of half d mean minus 1. So for example, if your d mean is t, then you will be able to correct up to error. How we do this encoding and how we do the decoding code? Suppose we have this message represented as a raw vector m and consists of message bit m0 1 mk minus 1, and then you are adding n minus k bits. So let it be represented by b, where b1 bn minus k minus 1, and together when them they constitute the code words, which is c0 c1 cn minus 1. Out of this n in the code word c, k are the message bits themselves and n minus k bits represented by this vector v, they are the redundant bits which are added in the coding process. Now we generate from the message bits and by a parity matrix P, where is a this m is 1 k, p is k into n minus k, and that will give us B this row which is 1 into n minus k. You can see that C is given as and M. Now in case of B, you can actually substitute MP. So M can be taken out and you get a new matrix which P, and these are unity matrix or unity matrix of size K. And together with these entries, it constitutes a new matrix G, which is called the matrix. So you get a code word C by multiplying the matrix G with the message M. With matrix H, which we define I n minus k, where I n minus k is again identity matrix of dimension n minus k, and we take P transpose itself was k into n minus k. Now this will be transposed when you take, so it will be n minus k into k. And you can show that H G transpose is 0. And therefore, if you now post multiply this C by H transpose, you get G transpose, mg H transpose, and this equal to 0. So this H, it is called the parity check matrix. And if you know, if you are using a G in the transmitter side and in the receiver, if you use the corresponding parity check matrix H, and if your code word is a valid code word transmitted without error, you should get C H transpose is equal to 0. So that is how you check whether the received code word is a valid code word. Now suppose the received vector R, it will consist of the code word you transmitted C and the error that has been introduced into the code word can also be written by a vector E of the same length. So please note, I have just used normal plus sign here, but whenever we are doing encoding, we are using modulo 2 always. Now if you multiply R with H transpose, then you will not get 0 until and unless E is 0. If there is a finite error, then you know that your HT into R is going to be different, because we said that G and H are made in such a way that CHT is equal to 0. Now what you are receiving is not C, but C plus E. So you will get another vector S, and this is called the syndrome, and the syndrome depends on the error pattern. And also you can show that the error pattern that by a code word has the same syndrome. For example, if you take an error pattern E and another error pattern which is E plus C, and then if you find the syndrome in both the cases, in the second case, CH transpose is going to be 0, and therefore you will get the same syndrome. From the knowledge of syndrome, error pattern can be found out. So this will just, I am not going into the complete or the details of this. I'll just show with an example. So if you know the syndrome and you know that from the knowledge of syndrome, error pattern can be found. You can find out what is the error pattern, and this error can be now used as a correction. For example, if you do modulo 2 addition of E on both the sides, R plus E, R is your received one, is C plus C is 0. So you get actually the valid code word. So if you know the syndrome and corresponding to that syndrome, what is the error pattern, you can do the error correction. We will illustrate this with some example. So let us see some, we have discussed a lot of theories. Let us see some examples. One very common code, commonly used code, is a repetition code where you repeat the same symbol. For example, a 1, instead of sending it as 1, you transmit it as 3 ones or 5 ones, like that. So we have n equal to 5 and k is equal to 1. So it is also a block code now with n equal to 5, k is equal to 1. And for this type of codes, your generating matrix is 1, 1, 1. These are the redundant bit you are adding, and this is the message bit. Corresponding parity Pumali, any issue? Hear me? Or I have lost the
Sir, you're
connection?
audible. No,
Yeah,
sir.
no, I
Yeah.
had a sound in between. I thought connection is lost.
No, sir. It's fine.
So, how you were constructing H? So here you can see identity matrix, and this 1, 1, 1, 1 transpose of this you put here, so you get your H. And here in this particular scheme, you have only 2 code words. Either you transmit all zeros or you transmit all ones, because your information is 1 bit, so you read only 2 codes, and you can verify that HG transpose is 0. Usually this type of encoding scheme, when used, the decoding become very simple. It is based on the majority rule. Suppose you are transmitting 5 bits and majority here will be at least 3. So if you are transmitting 5 once and at least you get to be 1, you make a decision in favor of 1 as the transmitted bit. If it is less than 3, you will make a decision in favor of 0. But try to understand, you can actually get good performance with this type of scheme. You can implement it easily. But what pay that to introduce the redundancy for transmission of 1 bit, you are transmitting actually 5 bits. So your code rate is very, very low. So the challenges in designing good code is that it should also offer high code rates, and it should be able to correct errors. It should be such that it can be implemented easily. I take another very popular code as an example, which is called a Hamming code. So Hamming codes are a class of linear block code where you have n equal to 2 to the power m minus 1, k is equal to 2 to the power m minus m minus 1, and d min is equal to 3. So that means you design a code such that minimum distance is 3 for m greater than equal to 2, and d min 3 means you can at least correct one error. For example, with m equal to 3, we have 7-4 Hamming code. Here you can see m equal to 3 means 7 and k will become 4. For m is equal to 4, we will have 15 Hamming code like that. And 7-4 Hamming code, this will be the generating matrix. And this will be the parity check. So our Hamming code it has a d min of 7-4 Hamming code, and that means it can correct one, and the code word length is 7. So that means it has 7 bit positions, and the error can occur in any of these 7 bit positions. And let us see if a single bit error occurs in any of these positions. Then what we can do, you can see that you leave this 0 0 0. If the error occurs in this position, remaining position error is not there, then the corresponding syndrome you can calculate. If the error is occurring in this position, you know that the syndrome is this. So when you receive information encoded in the 7-4 Hamming code form and it is transmitted, and after you receive this R, now you know the parity check matrix, you find out RH transpose, and then you will get S, this syndrome vector. And by observing what syndrome vector you are getting, know what is the error pattern if it is a single bit error. And once you know this error pattern, you can always modulo to add this to the received code vector and you can correct for error. So single bit errors can be taken care like this. And Hamming code is designed so that it can correct up to one error. If more than one error occurs, as I told, you are not sure what will happen. It may become a valid code word and it will go undetected. Let us very briefly discuss another type of codes which are very much used in practical communication systems. These are convolution code. Now, this codes, block code does not have a memory. It is block by block. You take first bit of first block of 4 bits, you encode it. Then you take the second block of 4 bits, you encode it to next 7 bits like that. And then you sequence them for transmission. But here, convolution code, they differ. Existence of memory in the coding scheme. Here also you have k bits mapped to n bits, but these are not only determined by the present k bits, also by the previous information bits. So let us try to understand the operation of this convolution code by a rate half convolution encoder. That means it takes one bit as input and produces two channel bits. And with a constant length of 3, L equal to 3. So that will be clear. We have a shift register here which holds the bit, and here you can see that the generating sequences in G1, all these three, they are modulo 2 added. In just give me one. In G2, you have 1, 0, 1. So input bit is not only a function of the current input bit, also a function of L minus 1 bit that precedes. So already you will have 2 bits present there from the previous transmission, and then you will add 1 bit here. So if the length of your shift register is, then L minus 1, 2 bits will get contribute to the encoding process. And here, if you consider, suppose these bits were 0, 0. Now the possibility is that incoming bit, it can be a 0 or it can be a 1. The next incoming bit is a 1. So we will move by, what will happen now? 1, 0, 1 plus 0 plus 0 modulo 2 to a 1, and 1 plus 1 in modulo 2, it will give again 1. This 1, 1 code is produced. So now what you shift this shift register to accommodate the next bit. So these two bits become 1, 0, because earlier bit was 1, and a new bit. So we represent this type of convolution codes in terms of an FSM finite state machine. So you can see that it has moved from state 0 0. It has produced the output of 1 1 for the channel. You sample both the output lines, and then you move to 1 0 shifted here, and then it takes another. Now this type of state transition diagram actually described the operation of the convolution. You can see that the output that you get here not only depends upon the present input, but what was positions, which are determined by the earlier uh, bits that entered. So memory, and it will keep on affecting the next 2 bits. What is present here will affect the next 2 bits, and then again these 2 will come here. So we have a constant length of L minus 1 if you are using a L bit shift register, and continuously the bits can come, and for each input bit you will get 2 samples in the code. For example, had it been, if it and the input is 0, then there is no change in state, it remains at 0 0, but you get at the output 0 0. So you can visualize that you will get a sequence of zeros and ones, every pair of 0 and 1 replacing one bit. Now this is at the transmitter. In the side you will get a sequence where some of the bits might have been altered by the noise present in the channel. Now, after observing this sequence in the receiver side, you will have to identify or make a decision about what sequence was transmitted from the transmitter. So this decoding of this type of codes difficult. Now, in order to formulate the decoding algorithm, usually another diagram is used, which is called a trellis diagram. As you can see that we are modeling it as a FSM, and it is going through different states depending upon these 2 initial bits and the next input bit. It is going only through a finite set of states, and trellis diagram represents the transition between various states as the time goes, how these states are traversed. Trellis diagram actually gives this. Also, you can have a transfer function gives the information about the through which the trellis start from all 0 state and return to the state for this. So in that way you can find out. Now, and he gave an algorithm which is known as, but it provides a maximum likelihood decoding for convolution codes. To discuss, because it will take lot of time. I'll just make a mention. Those who are interested can see any information theory or So it takes advantage of the Strelly structure, and when two paths enter the same state, the one having the best metric is chosen, and this path is called the surviving path. And in that tries to actually give a decoding which is in a sense maximum likelihood. I think I have already consumed my stipulated time, just half a minute. I will summarize. So we have discussed some of the very popular codes. There are many other codes like cyclic codes which form a subclass of linear block code. And this code has the property that any cyclic shift of a code word in the code is also another code word. Then another code, BCH code, belong to this cyclic. Reads of code, CRC or cyclic redundancy check codes. These are very much used in practical communication system. In fact, in all our packet transmission, we have CRC. Then recent times, lot of focus is on LDPC, low density parity check codes. Turbo codes was introduced around mid 90s, where actually you use two convolution encoder and an interleave. So these are all advanced coding schemes, but very used in communication system, and there are still lot of scopes of research in those areas, LDPC and turbo, because decoding complexity, how you can have less decoding complexity, how you can improve the error, all these issues are being investigated by people. So I hope in this short duration lecture, at least I could give you some overview of what are the types of way coding is used in the context of communication, and how the communication system design can benefit employing different coding schemes. With this, I stop sharing, and the queries already, I think I have consumed more than 5 minutes. Puvali, is there any query?
No, sir, no queries yet. Like one participants have written that it's a very great session, and the speaker is making complex issues very simple. So we are having a very good feedback, sir.
Okay, thank you. Thank you. So I do not keep Ribu waiting anymore. I think Ribu is already he's joining.
Yes, sir. Sir Ribhu sir has joined, sir.
Okay.
Yes, so I'm here.
Yeah.
So I pass the session over to you, Ribu. Thank you.
Yes, sir.
Thank you, Rataji sir, for the informative session. And with this, we'll start with the second session of today's lecture. So, Dr. Dr. Ribhu Chopra will be sharing his screen, and we'll start the lecture. Sir, over to you,
Yes.
Ribhu sir.
Yes. So I'll share my screen. So yes, is it? I hope it's visible. Okay, it's not visible right now. Screen 2. So is the screen visible now? So Viroza, is the screen visible?
Yes, sir, it is visible.
Excellent. So good morning, everyone. I'll be talking about the need and practicality of multi-carrier modulation, or as it is popularly known, OFDM, or OFDM is actually one specific example of multi-carrier modulation that we will cover, but we'll be talking about multi-carrier modulation in general. So to start, I hope all of you have at some point of time come across this expression, C equals log of 1 plus S by N. This was said to be the holy grail of communications, or actually this was derived by Shannon, and what he said that if you have an additive wide Gaussian noise channel, additive wide AWGN channel, then there exists a code that for a given SNR of S by N allows you to transmit half log 1 plus S by N bits per channel use. So these are bits per channel use, and if you allow a bandwidth, or if you allow a bandwidth W, then a bandwidth W actually allows you 2W channel uses per second. So you can get a channel capacity. So channel capacity is the maximum rate. You can get a channel capacity of W log 1 plus S by N, which is generally shown as the Shannon's channel capacity theorem. But the key idea over here is that this channel capacity is the maximum achievable rate that is possible over channel. However, practically we transmit at a slightly lower rate, something smaller, say R, that allows us to have practically manageable or small enough error rates. So while the channel capacity is the maximum achievable rate, we always operate at a rate below the channel capacity, and the margin, which I represent by capital gamma over here. So this gamma, or rather, this gamma here is known as the SNR margin. So we keep this as a margin that we operate slightly below the optimal SNR. So we operate at a rate R that is given as this half log 1 plus SNR by gamma per channel use, and consequently we can define the SNR margin as this beast, where so you can substitute into gamma for SNR, and you can reverse calculate this SNR over gamma from here, and then that gives you this. So SNR and S by N are the same thing. Fine. So, but if we use the channel capacity formula, or if we use a practical rate R, we make two, or this is under the assumption of an AWGN channel, that is an additive wide Gaussian noise channel. And an additive wide Gaussian noise channel in general makes these two idealizing assumptions. One, the SNR, or the signal to noise ratio that we can use, remains flat all throughout the channel. That is one. And we can transmit over an infinite bandwidth. Now, both of these assumptions become questionable under practical wireless channels. So wireline channels are a different story. I'll be talking mainly about the wireless channels right now. So under practical wireless channels, these assumptions become questionable. Because why these assumptions become questionable, we'll see. So to answer this, actually, we'll look at a wireless channel. So as we all know, a wireless multipath channel has multiple reflecting paths. So say suppose this small rod is the transmitter and the larger one is a receiver. So, and all these crosses are the multiple reflectors, scatterers, and other sources which act as obstacles in the path of electromagnetic propagation. Since also, in addition to scattering and reflection, we might also note that for these kind of channels, the for these kind of channels or for wireless communication, that the frequencies that we use that are of the order of several hundred megahertz or a few gigahertz, or rather I should say that 300 megahertz to 3 gigahertz, that is the currently preferred communication spectrum. So over those frequencies, what we note is that the obstacles, the size of the obstacles are large enough to cause diffraction of the bandwidth as well. So we have three effects: scattering, diffraction, and reflection. And because of that, say the the path due to we get h1 t tau 1. So sorry, if we transmit the signal xt after getting reflected from the first path, we receive the signal delayed by tau 1 and multiplied by a complex factor, or multiplied by gain ht tau 1. Similarly, for the second reflector, we transmit ht tau 2. We transmit the same signal, now delayed by tau 2 and multiplied with ht tau 2. Similarly, tau 3, tau 4, and there will be multiple such paths. However, so we can write that the received signal yt is the summation of all these paths. Note that all of this is in the absence of noise. Noise is an additional impairment that we'll have to deal with. But even without noise, we have that the received signal yt is hkt tau k and s t minus tau k. So if we consider this channel to be time invariant, that is the channel is independent of t, then we can write this as hk tau k plus, or rather I can write this part as summation over k tau k s. So I can write this as summation over k h tau k. Now here we can see that this basically is something like that I have a system with impulse response tau 1, tau 2, tau 3, tau 4, something like this. So this is tau and this is h tau. So having this kind of a channel is equivalent to having the signal that we are transmitting through the channel pass through such a system. This you can see is a finite impulse response system, an FIR system, and since it is an FIR system, it will have a frequency response. And what we see is that due to the different weights that are present at different times in the channel, this FIR filter is frequency selective, which is natural, that we have the channel, instead of being flat as we desired or as we assumed earlier, is now a frequency selective channel, which has an arbitrary frequency response. Please note that this is not the only frequency response that the channel can have. It can have any frequency response, and this is one realization of that arbitrary frequency response. So what this tells us is that our notion of a flat infinite SIN, so our notion of an infinite bandwidth flat channel is now questionable. We can no longer have a C equals W log 1 plus S by N and force W to infinity and transmit at negative SNRs. So that fundamental limit becomes questionable. So now practically, again, we have to deal with this kind of a channel. So how do we counter this? You might notice that this channel is slightly slowly varying in frequency. So one way, or the approach that is taken in multi-carrier modulation, obviously you can always take the equalization route. The equalization route involves taking the received signal and trying to process the channel or process the received signal so that the effects of the FIR filter are equalized away. That is one way of doing things, but that leads to ridiculously complex solutions. So we take another route. We say that this channel might be, yeah, we say that this channel might be slowly varying, but yeah, so the channel is slowly varying in frequency, which means that we are, yes, so the channel is slowly varying in frequency, which means that we can actually approximate this as a piecewise channel. That is, we can, yeah, that is, we can break the channel into multiple pieces and then use each of these sub channels as the main channel, or use each of these channels separately.
Hello, Ribhu sir. Hello, Ribhu sir.
Not audible, sir.
Hello. Actually, Ribhu sir's internet got disconnected, so he's trying to connect again. So please be patient and stay connected. He will be connecting in another 5 minutes. Thank you.
Yeah, am I audible now?
Yes, sir, you're audible.
Yeah, so somehow my internet window that timed out,
Yeah.
and I
No
sorry
issues, sir.
sorry
Yeah,
for the
no issues,
interruption.
sir.
So I'll continue.
Yes, sir.
Yes. So sorry everyone for the interruption. Somehow my internet got disconnected. So yes, what we will do here now is basically split the entire channel into sub-channels and transmit separately over each of those sub-channels. That is called multi-carrier modulation. That is, we transmit over each of the sub-channels via a different carrier. And this is called multi-carrier. Multi-carrier modulation. Since we are using multiple carriers. Fine. So the idea is that the incoming data stream is split into n substreams, and the kth substream is modulated using the carrier phi k such that phi k is given as phi t e to the power j 2 pi fkt. Fkt is the carrier of the kth subcarrier's frequency. Fkt is the kth subcarrier's frequency, and phi t in general, or for the purpose of this discussion, we assume that phi t is root 2 over t, sinc of t over capital T, where t is the symbol interval, or this is the capital T is the symbol capital T is the symbol duration. Fine. So now, based on this, phi f is root over t rect of ft, and phi kt can be written as this. Fine. So this is a solution. Now, what does this mean? This means that if we have a stream of bits, then we split that stream of bits into n substreams like this, and we transmit all of those streams over separate subcarriers. Obviously, this symbol mapping, this indicates that these are sent as separate symbols. Note that for the purpose of this discussion, we will assume that all the symbols come from the same constellation, but practically all these symbols need not come from the same constellation, and maybe from different constellations as well. But for the purpose of this discussion, let us assume that all these symbols come from the same constellation. So we split the stream of bits into n streams and map each of those streams to symbols. Now, it is also easy to show that phi kt for k goes from 1 to capital N forms an orthonormal set. We have discussed what are orthonormal sets in the previous discussion, and the proof is rather simple but detailed. So what is there that if you look at the frequency domain symbols, yeah, if you look at this, so we observe that this rect t of f minus fkt, this will be so this will be orthogonal if the frequencies are separated by 1 over k, since this is non-zero only within a duration 1 over, or only within frequencies 1 over t. So this will be these will be orthogonal, and consequently, yeah, sorry. So and consequently, we can say that the in the frequency domain, these signals are orthogonal, and since these signals are orthogonal in the frequency domain, they are orthogonal in the time domain, since the orthogonality remains unchanged over orthogonal transmission, orthogonal translation, or orthogonal transformations. Oh, sorry, yeah, the since the Fourier transform is a linear transformation and orthogonality remains unchanged under linear transformations, so the signals are still orthogonal. And therefore, since HKF is HF times this means that multiplying with different phi k's actually splits the channel bandwidth HF into n non-overlapping subchannels. So what we are doing here is that by using this kind of a basis function, we are splitting the channel HF into n orthogonal n non-overlapping subchannels. That is precisely this, that or whatever I have done there is actually precisely splitting this channel into n. So these are non-overlapping subchannels. So by multiplying with that kind of a basis function, we are splitting the channel into n non-overlapping subchannels. And we assume that the channel, so you can see here that the channel remains constant during each, or the channel variation is small during each subchannel, or for each subchannel, the channel variation is small enough. So we can say that each subchannel is constant. So based on this, we can write HKF as HK. That is, you have a channel coefficient, and the frequency, the channel response doesn't change around that HK. So this is true. and this should have been non-overlapping partition, or simply a partition of the channel frequency response, since partitions are by definition non-overlapping. So now letting xk be the symbol sent over the kth channel, and also since the frequencies are separated by 1 over t, we can write fk as fc plus k over t, where fc is the starting frequency. Or again, if I look at it, this is fc, this is fc plus and so on. This is possibly fc plus n minus 1. Fine. Therefore, yes. So now the overall modulated symbol can be represented as xt equals k goes from 1 to capital N, real of xk. So since x symbol sent over the kth channel, e to the power j 2 pi fkt, which is nothing but the real part of, so real part and summation are both linear operations. We can interchange them without any problems. So this is the overall modulated symbol is real part of summation of k goes from 1 to capital N xk e to the power j 2 pi kt by t 2 pi fct. This. So we have this. Now, invoking the discussion on low pass equivalents from 2 lectures earlier, we can see that this xt can also be written as real part of xl t j. Fine. We can write this as a low pass equivalent, and based on this, the low pass equivalent takes this form: xlt equals k goes from 1 to capital N xk e to the power j 2 pi kt by t. So now we see that this xt is periodic, or this xl of t, the low pass equivalent, is periodic, because e to the power j 2 pi kt divided by t, this is basically a complex sinusoid excuse my handwriting, frequency k by t. So this is a complex sinusoid of frequency k by t. So basically all of these are harmonics of the same signal. So we have okay, so this should be 0 to n minus 1. That is a typo because of the way we defined it. Yeah, so no, so my bad. So I should have here, this is fc plus 1 over t, and the fc lies somewhere over here, and this should be fc plus n over t. My bad. So yeah, anyway, coming back. Yeah, so this is a complex sinusoid with frequency KOT. XLT is periodic, and we can convey the entire information by transmitting one period of this periodic signal over time, because since the signal is periodic, all its periods contain the same information, and the entire information can be conveyed by transmitting one period over time t. And XLT can be obtained via NXK. So basically, if we know XKs, we can construct XLT, or in other words, since XLT is now an equation in XK, if we take n samples of XLT, that can be used to construct reconstruct XL, since it has a limited frequency and complex valued. So XLT can be reconstructed from its n samples. So now let XLN be this. So XLN, the frequency domain, this looks like this thing. So I believe all of you know this form. We have all encountered this form, that XLN equals xk e to the power j 2 pi kn divided by n. So this is the discrete Fourier transform. So if we take the symbols xk in the frequency domain and take their inverse, oh sorry, this is the inverse Fourier, the discrete inverse Fourier transform, not the discrete Fourier transform. So if we take the symbols in the frequency domain and then try to map them to the time domain using the inverse Fourier transform, we get a time domain signal, and after interpolating XLN, yes, after interpolating XLN, we can get XLT from these n samples, and this being the discrete Fourier transform can be implemented quickly using the inverse fast Fourier transform. So we can actually invoke the fast Fourier transform algorithm to generate XLN. Fine. So now we have a mechanism of generating a carrier, or we now have a mechanism for generating multi-carrier modulation, that is, take the symbols in the frequency domain, and after taking those symbols in the frequency domain, simply take the inverse Fourier transform of all those symbols together, and you will get a time domain signal that will contain all that information, and then you can pass that time domain information through the channel, and you get the frequency, and you get back and at the receiver, if you take the Fourier transform again, you will get those symbols back. So now, based on this, let the symbol sent over the kth channel be xk. Then it will be multiplied with the, since we are considering a discrete Fourier transform, we are considering a discrete DFT like operation at the receiver as well. The received symbol will become yk equals hkxk plus wk. So wk is the additive white Gaussian noise. So wk is the additive white Gaussian noise, and Now, the received symbol can be easily reconstructed from sorry, this xk can easily be recovered from hk, this yk. And now let the power allocated to the kth symbol be pk. And let the rate achievable over the kth channel be rk. Then the question that we have is, or how do we calculate the rate? So we know that what we discussed in the start of this lecture, this is the achievable rate. And based on this, the overall average rate throughout n channels can easily be calculated as 1 over n. So there are n channels, we simply calculate the mathematical average, nothing much. So that can be written as 1 over n times, that can be written as 1 over n times log to the base 2 1 plus hk this, and that can be reduced to, so since summation of logs is equal to product of the arguments, so I simply move the summation inside, and 1 over n becomes 1 to the power n, product this 1 over n this, and the effective SINR can be represented as this. So we are halfway through the presentation, or we are halfway through this lecture. So if there are any questions regarding this, I'll be happy to have them right now. So what I will do is, I will expand the window. So yes. So just a second. Firoza, I'm logging in from another laptop, so I will be able to see the questions that way.
Yeah.
So
Okay.
if there are questions, let me in. And if there are questions, I'll attend to those and then continue.
Okay, sir. So in the same screen also, you'll be able to see the questions, sir.
Okay, I am not able to actually. That's why I'm using the other laptop. So that is logging in. So stop
Okay, sir.
video, join event. So I'm logging in. Please let me in and don't make me a presenter. I should just be able to see the chat.
Okay, sir. Okay.
Yes. YFFT8 transmitter, and so the answer is that see, one thing is the original signals are in the frequency domain, or if you look at the channel, we are basically trying to split the channel in the frequency domain, right? But practically we operate in the time domain. So we are splitting the channel in the frequency domain. So we are transmitting different symbols in the frequency domain, but we are still operating in the time domain. So to make those frequency domain symbols realizable and sendable in the time domain, we use this inverse Fourier transform operation, so that we map the symbols from the frequency domain to the time domain that can be sent over as a waveform. And at the receiver, we now get a time domain signal which contains garbled up symbols from the frequency domain. So in order to retrieve those symbols in the frequency domain, we need to take the FFT again. so that those symbols again get mapped to the frequency domain and we can play around with them. So Lokishyam, I hope that answers your question. Then I will answer Ravi's question. So you can send a thumbs up. Yeah, excellent. So next is, yes, so we will, can you suggest some good links material so that I can learn the concept and do hands-on? So Abdul, our purpose is to be one of those links. Otherwise, there's a lot of material available on NPTEL regarding OFDM. So maybe, yes, regarding all these topics, since these are quick refreshers in this direction, maybe this material is not detailed enough, but we are trying our best. And so how do we find the, okay, so how do we find, Ravi Kumar Goyal, how do we find the channel coefficient HK? So channel coefficient HK is actually estimated. That we need proper pilot training. So we need to insert pilots at different positions. We need to transmit pilots. We need, so there are two ways of doing that. We can either send a pilot OFDM symbol, or, so actually let me open Word. Yes, and just a second, Word, yeah, Word is here. So yes, so I will, because I hadn't I hadn't thought of this in the presentation, that but this is a good question nonetheless, so I'll answer it right now. So okay, so maybe I need to close this. Second, Word is opening, so this, yeah, so okay, so yeah, so maybe Word isn't a good idea right now. So yes, anyway, so to answer your question, what we do is we transmit pilots and use pilot based training to send symbols, use pilot based training to estimate all these sub channels. The good part about that is that what we do is we can insert pilots, so different OFDM symbols can have pilots placed at different locations. So suppose this can be a pilot, this can be a pilot. Yeah, any of these can be a pilot, and what I can simply do is estimate this. So now if these are slowly varying, that is, you can see that if I know this, say this is 1, 2, 3, 4, 5. So if I know the fourth block, I know the third and the fifth block. Similarly, if I know the second block, I can closely approximate the first and the third block. So these channels are slowly varying. So instead of estimating each sub-channel separately, I can alternatively use multiple pilots, or I can use pilots just in some strategic locations so that I'm able to estimate all the channels nearby, but separate pilot based estimation is required. A lot of work has been done on this in the early 2000s, but that goes beyond the scope of this presentation. So that's all I would say right now, but how to maintain orthogonality while splitting. So see, this ensures this thing. Splitting orthogonality is ensured due to the structure of the signal. So this phi f t rect of ft. So for a symbol duration t, these phi kt's are orthogonal, or in the frequency domain, you can see that for a symbol duration t, these phi kt's are non-overlapping. So since these are non-overlapping means orthogonal. So since these are non-overlapping, these are orthogonal, and when you go from the time domain to the frequency domain, there is a result, the Parseval's relationships. So Parseval's relationships basically say that something that is orthogonal in the time domain is also orthogonal in the frequency domain. That is a separate that's maybe a 10-minute proof, but we don't have that over here. So I assume that Parseval's relationships are true, and using Parseval's relationships, we maintain this orthogonality in the time domain. So Dukisham, again, does that answer your question? Yeah, excellent. So Ravi, if I have answered your question, maybe we can move forward. You can just give a thumbs up and we can continue. Yeah, excellent. So I will continue. So now we had this overall average rate and the effective SINR. So sorry, the effective SNR. That is, we can calculate the effective signal to noise ratio based on this. And now we want to maximize the we want to maximize the average achievable rate. That is, we want to maximize the, obviously that's what we are after since the beginning, that we want to maximize the number of bits that we are able to transmit per second. So the simple answer to this question is to put in more power, or the more power we transmit, the better rates we achieve. That's what actually what the channel capacity theorem says, that it's half of log 1 plus s by n. So the more SNR, so you cannot control the noise power, you can only control the signal power. So the more signal power you pump in, the more the better the achievable rate will be for you. Fine. So the simple answer is to put in more power, but we always have written limited power budgets. We cannot simply go on paying more and more for electricity. That's a bad idea, because that also harms the environment. So we are limited by a power constraint. And since we are limited by a power constraint, the problem is to maximize the achievable rate. The problem is to maximize the yes, the problem is to maximize the achievable rate given a transmit power. That I tell you that I can transmit some 100 megawatts of power. 100 megawatts is a bit too much, but I tell you that I can transmit maybe 10 kilowatts of power, and I want to get the maximum achievable rate. That's what engineering design is, that you have some power and you maximize the achievable rate. So in that case, the problem at hand becomes maximize this achievable rate. So this is the achievable rate expression. Maximize this achievable rate for the K channels such that the total power is limited at P. Fine. So we have a constrained optimization problem at our hand. So since we have a constrained optimization problem, we have to solve this. But now the question is, how do we solve this? So the first thing that we notice is that this is linear. And the log function is concave. So we have two good things. The log function is concave and the constraints are linear. So that allow us to use standard optimization techniques or analytical optimization techniques to solve this problem. So we invoke the method of Lagrange multipliers. You might have encountered this method, that is the method of Lagrange multipliers, in class 11th. So that is where we teach this first, that we have some constraint plus some equation. So the method of Lagrange multiplier simply states this, that if you have a function fx that you want to optimize with respect to some constraint gx, then you write it the optimization function as jx as f, gx plus fx plus g lambda x, or lambda of gx. So this is the equation in Lagrange multipliers. And when we try to solve this equation, or now in order to maximize this, we show that we get this beast. Fine. So we get this, and after setting this to 0, because obviously the maximum is at 0 for each Pn. So we have to set this to 0 for each Pn. The maximum is at 0 for each Pn, and therefore for each Pn we get this. Now defining so interchanging these terms and defining 1 over 2n log to the base 2e divided by lambda as mu, what I can do is I can write Pn plus gamma n naught divided by t. So n naught divided by t is the, or n naught by t is the power, noise power. So that I believe I should clarify that yeah, so n naught by t is the noise power. So n naught is the noise power spectral density, 1 over t is the bandwidth, and therefore noise power is n naught by t. So this is n naught by t, and so Pn is gamma n naught by t hk square. This equals mu, and Pn equals mu minus this beast. And we also have this constraint that mu minus gamma n naught by thk, this thing for all k equals p. Now once we try to solve this, this is known as the water filling algorithm, and we see that when we try to solve this, not all subcarriers or not all pKs will be positive after this. So when we try to solve this, not all PNs, yeah, since we use K, so my bad, yeah, this should be N. Yeah, so not all PNs should be positive, and based on that, since not all PNs are positive, what we do is we ignore the negative PNs and take only the positive powers. This is known as water filling. And finally, after this, so there are certain null subcarriers, some subcarriers which are so bad that we don't want to transmit over them. So this, for example, if you consider this to be noise floor, that you don't want to transmit any subcarrier that is worse than this. So these three, in that case, will become null subcarriers, that these are not performing at par with what you want, and you are, if you try to transmit data over these, you are spending too much power, so you don't spend any power on these. And so this is like filling water above this level. So that's why this is called the water filling solution. And based on this, what we finally have is the final OFDM signal. So we have a bunch of symbols. We have a bunch of symbols AK. So capital K is less than capital N. So this K is the number of subcarriers that are actually allocated symbols. With symbols. Then you insert pilots and vacant subcarriers. You do this, you get something like this, and this is the time domain OFDM signal. This is the time domain of the OFDM signal that we were waiting for. Now you do D2A conversion and you get this. So this is what the final OFDM symbol looks like. Fine, but this is not the end of the story. The problem is that we started off with countering, or we started off in an idea with an idea to counter the intersymbol interference. Intersymbol interference, if you might remember, is the interference between two symbols that exist due to this finite impulse response behavior of the channel. Because what happens is that while you are still receiving parts from one symbol, or the reflections and the late effects of one symbol, other symbols may come into play, and they start, yes, other symbols may come into play, and they start wreaking havoc with the present. So yeah, Lokisham, I got your comment right just now, that explain a way to use water filling. So water filling is actually a mathematical. So the fun thing is that a lot of practical algorithms have been given catchy names. So water filling is nothing but solving, or this is called the water filling solution. This solution repeatedly, these should be n's. Should be n's. Yes. Yeah. Solving this repeatedly, removing the negative powers, is called the water filling algorithm. There is nothing else to it. just that it has been given a fancy name. I hope that answers your question. Or if you would want more clarification, or if there is any specific point that I'm missing, you can tell me that. How to remove? Simply how to remove is simply you consider this k equal to 1 to n, set those to 0, set pk to 0 for that. You can always remove terms from a summation, right? You can remove terms from a summation, and since you can remove terms from a summation, you can avoid using sum carriers. I hope that makes sense to you. Yeah, thank you. So coming back, so again, yes, so we had this. So the intersymbol interference still exists, and since there is still intersymbol interference even after OFDM, what we have to do is, yeah, so since intersymbol interference exists even with OFDM, so one symbol will try to interfere with the next symbol. So what we have to do is insert a guard interval. That is, say the channel delay spread is tau max, then we insert a guard interval delta G such that this delta G, or the OFDM symbol, actually consists of the small ts and the total time, capital T, that we were talking about since long, T equals delta G plus Ts. So we actually lose something in order to avoid ISI. So that is the need for guard intervals. But that's not all about guard intervals. So what we are doing is we are using DFT at both the transmitter and the receiver. And we all know that DFT actually results in circular convolution, or DFT actually works by taking periodic extensions of a signal. So since DFT works by taking periodic extensions of a signal, it results in circular convolution. So when we try to deconvolve at the receiver, that is when we try to remove this interval and take the FFT, remove the guard interval and take the FFT, it will try, the ISI will cause, it will expect that those channels have, or it will try to deconstruct this OFDM signal based on the assumption that the channel was circularly convolving with the signal and with the OFDM signal and not linearly convolving, as we are assuming. Since we are assuming a circular deconvolution and we have a linear convolution, we have to force the linear convolution operation to be circular. So, and circular convolution involves convolution with itself. That is, you take the tail of the signal and put it at the head. So that's why we, instead of using a plain old guard interval, what we do is we instead take the end part of the symbol and insert it in the beginning. So we take the end and insert it in the beginning, and so this OFDM symbol, instead of being extended by zeros, actually is extended by its cyclic extension. So you take this and add this. So This is actually the same as this end, and sorry, slightly bad, but just a second. It is this end. This need not be continuous. These are samples. This. So you insert the tail of the symbol back here, and that is known as the cyclic prefix that allows smooth OFDM operation. Fine. So now these are the final characteristics of an OFDM symbol that we want to talk about. The effective symbol period is TS, small ts, that is capital TS minus delta G. So you can say that the spectral efficiency is, so we are not still working at 100% efficiency. We lose something to this cyclic prefix. The intercarrier spacing or the spacing between two carriers is now naturally 1 over small ts. The transmission rate is 1 over capital TS, which is obvious. The transmission bandwidth is this, which makes sense. And the guide interval factor is delta G over TS, which is basically 1 minus the efficiency. Fine. And the final form of the OFDM transmitter looks something like this. We have input data. We do some symbol mapping. We do parallel to serial conversion. We insert pilots. And actually we optimize power as well. We do the IFT operation. Then we do serial to parallel conversion for serially sending it. And then we do, so we get basically, these are XKs, we generate XKs. We convert these XKs to, so these are the XKs, you can say. So IFFT, we get XN here. And then we do digital to analog conversion, we get XT or XLT, low pass equivalent. And after we get XLT, we insert the guide interval and the cyclic prefix, and then we mix it with the carrier and transmit. Now the questions, or now the choices that we have to make. One, how many subcarriers? You might be tempted to say that the channel is, yes, we might be tempted to say that the channel is continuous. So we want more and more subcarriers, or we say that the more subcarriers we split the channel into, the better response that we get theoretically, right? But the caveat here is that, or the smaller the inter-subcarrier spacing, the flatter will be the channel and the better will be the response, and we can transmit multiple pilots. So n should go to infinity. But at the same time, we see that as we increase the number of subcarriers, as the number of subcarriers goes to infinity, the time duration. So you might see that in the previous slide, this won't be easy. So yeah. So here you might see that the time duration increases as we, okay, that's not here. So, but you can see that the time duration increases as we increase the number of subcarriers. So what might end up happening is that the symbol becomes too long for us to handle. or the symbol actually becomes too long for the channel to handle, since the channel has something called coherence time. So if the symbol duration is so long that the entire symbol doesn't fit into the coherence time, then you're doomed, because you won't be able to make anything meaningful out of it. The second question is the guard interval. Oh, sorry. But make the symbol too small in time, and the subcarrier spacing will be too large. You won't get a flat enough channel. The channel will be larger than the coherence bandwidth. So the optimum here is that you make the number of subcarriers such that the symbol duration is smaller than the channel duration, and at the same time the channel is and at the same time you get flat enough channels. So that addresses the choice of the number of subcarriers. The second choice is the guard interval. You make the guard interval too long, and you run the risk of having to deal with you run the risk of having a too low an efficiency. So you can have the guard interval equal to the length of an OFDM symbol, fine enough, but that will lead in a small efficiency that you are only using half of the efficiency that was supposed to be used. So that is bad from a bandwidth efficiency kind of a perspective. But at the same time, if the guard interval is too small, then what happens is that if the guard interval is too small, then what will happen is that there will be ISI. One symbol will interfere with another and cause problems, which is again not a good thing. Then pilots. How many pilots? Too many pilots, again reduced efficiency. And too few pilots, you get bad channel estimates and aren't able to decode anything. Positions where to place these pilots so that you get optimal response. So all these problems actually are separate research problems in literature, and extensive work has been carried out on these in the late 1990s and the early 2000s. Someone interested can go back and have a look. But since each of these problems itself becomes a 1-hour talk, so I'm not going into the details of these problems. I'm just telling you that there is something like this out there. But now OFDM isn't all rosy. That is, we discussed the theoretical concept behind OFDM, and we discussed the problem of we discussed the choices that we have to make. But there are certain challenges that are unique to OFDM that arise due to the specific structure of OFDM. So now we have synchronization, we have clocks, and everything is based on local oscillator and carrier frequency. But we are at the modulator and the demodulator, we are assuming that both the transmitter and the receiver know the carrier frequency exactly. But practically what might happen, there might be a slight drift in the carrier frequency. The local oscillators may change. And when the local oscillators change, the first thing that happens is that each subcarrier will be slightly shifted. And now since each subcarrier is slightly shifted, you lose orthogonality. And the moment you lose orthogonality, there is intercarrier interference. So the data that is sent over one carrier will now interfere over another carrier. So that causes intercarrier interference, and that is a separate research topic in OFDM, and that can lead to potentially catastrophic errors in OFDM. Similarly, for constant modulus constellations, or till before OFDM, we dealt with kind of constant envelope constellations or constellations that worked at a few levels, and we could get away with using simple power amplifiers. But a practical OFDM waveform actually looks like this, which is a highly varying long dynamic range waveform. So you cannot use cheap power amplifiers. You cannot use power amplifiers that have a small linear region to work on these, because This will again cause distortions in the OFDM signal, which will lead to noise. So this issue is known as the peak to average power ratio. That is, for most constellations, BPSK, QPSK, QAM, the average power is close to the peak power for finite QAM, like 16 QAM. The average power and the peak power are not much different. But in case of OFDM, the peak power and the average power can be hugely different. The waveform can suddenly shoot up arbitrarily, leading to a large peak to average power ratio, which causes the power amplifier to work in the nonlinear region, and that subsequently causes a distortion in the received signal, further causing an error in the received signals. So, or an error in the decoded symbols. That is another problem. So with these, I would like to list out certain practical applications for OFDM. So OFDM is practically used in digital audio video broadcasting, 5 gigahertz wireless LAN, 3G LTE, 802.11G and 802.6. So 802.11G is Wi-Fi. Wi-Fi, actually this is 4G LTE. Wi-Fi, and this is now discontinued, but erstwhile popular, WiMAX. And these are the standards of OFDM used in LTE. So for LTE, you have a subcarrier spacing of 15 kilohertz, a subframe duration of 1 millisecond, a sampling frequency of these possible values, an FFT size of these values corresponding to those sampling frequencies, and number of data subcarriers given as these. So you can see that the total number of subcarriers to data subcarriers is around 60-ish%, close to 60%. So that is the kind of efficiency that we expect in OFDM. And so this was all. And I see that I have 5 minutes left because because of the outage. So I had expected a 10-minute session after the talk, but because of the slight power outage, because of the internet outage, we are left with slightly less time. So, but we still have time for a couple of questions. So in case there are no more questions from the second half of the presentation, we can end this. Oh, there are questions. So 802.11a, so these are all generations of Wi-Fi. You can go to, so these are long standards actually, and quite boring. I honestly do not remember these. So OFDM is used there, that I know, but the precise details, you will have to use Google for that. I do not remember those details. Okay, so in case there are no more questions, we can possibly end this session.
Yeah. Thank you, Rebu sir.
Thank you.
For the wonderful session.
Yeah. Yes. Thank you again, and sorry for the internet glitch. I should have kept the
No
window
problem,
open.
sir. So it's a common thing that we all have to face.
Yes. Okay. Thank you.
Thank you, sir. So with this, we come to the end of the second session of today's program. So we'll start with the third session, and the third session will be presented by Dr. Kalpana Dhaka ma'am. So Kalpana ma'am, I request you to please start with the session.
Yeah, I'll share the slides once again.
Yeah, okay ma'am.
Slides are visible now?
Yes ma'am, it is visible.
When should I start?
Ma'am, you may start.
Okay.
Ma'am, whenever you feel comfortable, you may start.
Okay.
Yeah, thank you ma'am.
Because the previous session just ended, so that's why I am asking whether there is a break or it is in continuation.
No ma'am, there is no such break, or ma'am, if we can take a break of 2 minutes. It's 11:59 and then we may start.
Okay, fine.
Yeah. So participants will be starting after 2 minutes. So if you want a break, please take a break, but please stay connected. We'll start in 2 minutes. Thank you.
Okay, can I start now?
Yes, ma'am, we may start.
Okay, so I'll be talking about spread spectrum and direct sequence spread spectrum in this lecture. So these are the texts that I referred. One is Wireless Communication by A. Goldsmith, and other book is Principle of Mobile Communication by Stuber. So spread spectrum, or the term, was originally developed. This technique was initially developed for military application to provide anti-jam and low probability of intercept communication by spreading signal over large frequency band. So in spread spectrum, what is basically done is a signal is basically spreaded over a wider bandwidth using PN sequence code. So this PN sequence code is unique. So the initial development of this technique was for military application. It started with that as an application in mind. It provided anti-jam and low probability of intercept communication. Since it has unique code, so that's why it provided intercept communication. For detection, it required a unique code at the receiver. So that's why it provided anti-jam and low probability of intercept communication by spreading signal over very large frequency band. The advantage of what it does is it hides signal below the disadvantage. It hides signal below noise floor, making it difficult to detect. Since we are spreading the signal over a wider bandwidth, the overall energy over the wider bandwidth, the signal energy reduces on spreading, so it may the signal may hide below the noise floor on spreading. So that is the disadvantage of spreading the signal here, which makes it difficult to detect at the receiver. So the other thing is it transmits low power per unit bandwidth. So over the channel, the signal has lower power per unit bandwidth. The bandwidth of spread spectrum signal is much larger than the message bandwidth. So the features of spreaded signal is that it has wider bandwidth and is communicated at lower power. And the application includes CDMA, wideband CDMA, CDMA 2000. It also includes, the other application includes wireless LAN standards such as IEEE 801.11, that is for the Wi-Fi system, wireless personal area networks such as Bluetooth. So these are a few of the application of this. The advantage of this technique is, of spread spectrum technique is, it provides universal frequency reuse. All user uses the entire bandwidth for communication. Each user is assigned the entire bandwidth for communicating with the other user. Other feature is narrowband interference rejection. So since we are spreading and despreading the sequence, so the portion which is there in the on despreading, the portion which is in the band other than corresponding to the so on despreading, major portion of the interference get removed. We'll see how this happens. Then other feature is inherent multipath diversity in DS spread spectrum. For this thing, for detection at the receiver, we use rake receiver, which combines the signal which is propagated through multiple paths, and the combining is done using maximum ratio combining. So it exploits the diversity advantage on communication over the channel. It has ability to exploit variable rate speech coding. So based on requirement, the data rate can be changed. It provides soft handoff capability. Since we are each channel or each user is using the entire bandwidth, so there is no change in the channel. So that's why it offers soft handoff. Then the number of PN sequence can be you can have, in order to accommodate more users, you can increase the number of PN sequence that are used. So it has soft capacity limit. By increasing the number of PN sequence, you can accommodate more number of users. Inherent message privacy, since the PN sequence that is used for spreading, that is unique. So that's why it offers an inherent message privacy. The disadvantage of spreading here are stringent power control requirement with DSCDMA. Since a wider bandwidth, the signal is spreaded over the wider bandwidth, the energy, there is rapid variation in the energy strength. So because of that, it's difficult to control the power requirement in DSCDMA system. There are difficulties in determining the base station power level for deployment that have cells of different sizes. So in the systems where irregular cell sizes are there, it's difficult to determine what is the right power to be transmitted at the base station. The properties of spread spectrum modulated signal are: the signal occupies a bandwidth much larger than what is needed for the information signal. So since we are spreading the information signal, so the bandwidth of the spreaded signal is very high as compared to the information signal. Modulated using a spreading code. So this message signal is modulated using a spreading code which is independent of data in the signal. And so the spreading code is independent of whatever is information in this information signal. So data in the spreading code is independent of data in the information signal. At the receiver, despreading is done by correlating the received signal with a synchronized copy of the same spreading code. So whatever spreading code is used at the transmitter for modulating the information signal is required at the receiver side. For the understanding purpose, an example is represented here. If we are transmitting a signal SIT, that is your message information signal. So if an information signal SIT is transmitted, the received signal in presence of interfering signal IT is, so if IT is your interfering signal, SIT is your message signal, then overall signal will be XT. So here SIT, that is the information signal. So SIT is transmitted, consider SIT is transmitted, the received signal in presence of interfering signal IT is, where SIT is equivalent to, so here SIT is basically sum of or n orthogonal bases. IT is the information interference signal, which again is a combination of n orthogonal bases and projection of interference in those n direction, and T is the overall time period. SIG and IJ are coefficient representing the projection of SIT, that is signal and interference on the basis function phi gt respectively. The output of the correlator at the ith branch of the receiver is, so here at the receiving side, the received signal, that is xt, which is the combination of transmitted information signal and the interference, is can be represented at the input of correlator as xi is equivalent to 0 to t xt sit dt. So here at the receiver, the correlated the received signal is multiplied with the corresponding one of the signal level and can be written as, so this is sum of the projections. Here, since we are considering n directional orthogonal signal, we can rewrite this as, so here we have n basis function are used. So this signal can be rewritten in this form. The signal to interference power ratio SIR is given by, so using this we have the signal power is there and then the interference power. So the ratio of the two is given by signal to interference ratio. Here we have signal energy is given by sum of all the projection. Signal energy is given by this expression where this is the desired signal energy, that is projection in the direction of you can say whatever spreading code is used. So if the desired it matches with the desired spreading code, then you have, this is your signal energy and this is the interference energy. which is other than the signal energy. The projection in direction other than the signal direction is your interference power. Is the energy of the interfering signal. Here n is equivalent to 2 bst and m is equals to 2 bt, where bs is the transmit signal bandwidth and b information signal bandwidth. So here we have signal bandwidth. We assume that it is greater than the information signal bandwidth. So here, spreading interference power over larger dimension n other than the required signaling dimension m, the SIR is increased by a factor G, that is processing gain, that is a ratio of n by m and is given by bs by b. So that is the ratio of basically the signal bandwidth to the information signaling bandwidth. So this processing gain is determined by these two parameters. Now, G is known as the processing gain or the spreading factor. The underlying meaning of processing gain is generally related to the performance improvement of a spread spectrum system relative to a non-spread system in the presence of interference. There are two types of spread spectrum technique, that is direct sequence and frequency hop spread spectrum. So in the direct sequence, it achieves the band spread using a PN sequence to introduce rapid phase transition into the carrier containing the data. So here, n number of PN sequences are used in order to isolate the information carried over different carriers. It mitigates the intersymbol interference when the unmodulated signal is spread over a wider bandwidth. So here, because of spreading the signal and despreading it, you can automatically get rid of the intersymbol interference when the modulated signal is spread over a wider bandwidth. So that is a feature of this DSSS. Then frequency hop spread spectrum achieves the band spread using PN sequence to pseudo-randomly hop the carrier frequency throughout a larger band. So here a random PN sequence is used. So you have, if n is the size of PN sequence, so based on you'll hope for n different frequency baseband frequency levels in frequency hop spread spectrum. So you switch between the different frequency. And in the first one, PN sequence, you have n number of PN sequences are there, which are multiplied with the information signal, and this information signal is spreaded over a wider bandwidth. Whereas in frequency hop spread spectrum, information signal is repeated using the PN sequence code, which basically is used to hop among different frequencies. So FHSS protect each symbol against narrowband interference and spectral nulls due to frequency selective fading. Now, how this spreading is done will be discussed here. So since consider a narrowband signal, that is baseband modulated signal xt, which has duration t of s. So it is a narrowband signal which is multiplied by passband modulated signal of st. So this is the baseband modulated signal. This is passband modulated signal st and the spreading sequence. So here this st is multiplied with sct. So when these two signals are multiplied, here the symbol duration is very large as compared to this chip duration. You can accommodate a large number of TCs, very small as compared to your symbol duration. So this is baseband modulated signal. So this will be repeated based on the information. So in every TC value, this pulse will be considered. So if 1 is there, your baseband modulated signal xt will be there. If 0 is there, then accordingly your level will be 0. So here transmitted signal, and this is baseband and the passband. So here based on since this is 1, so based on this signal, this is represented. This is multiplied with this, and you'll get this transmitted signal, which is actually communicated over the channel. Now, direct sequence spread spectrum model, system model, in-phase signaling in a DSSS system is given by this system model. A similar structure follows for the quadrature phase signaling. So here in-phase signaling is represented. So similarly, the quadrature signaling will be there. So in the in-phase signaling, in-phase component of transmitted information is passed through this pulse shaping filter. So this XT is your actual information, which is multiplied with SCT, that is spreading code generator information. So this XT is spreaded using this, then is modulated, and then it is communicated over the channel. Over the channel, the signal is combined with noise as well as interference and is received at the receiver. So RT is received at the receiver. Now, at the receiver, you need to do the demodulation. Whatever processes you have followed here, you need to reverse that. So you need to use demodulation. Then the spreading sequence code is used. You need to reverse the or use the same spreading code in order to estimate the transmitted information. So XT was transmitted. So now the estimate of transmitted information is XT. Now this was GT is your pulse shaper that was used. So here in order to get symbols back, reverse of this match filter is used here, and then the outcome is passed through a decision device in order to estimate the digital information that is communicated. So this is expressed by these points. So at the transmitting end, so this is the same thing. The system model is explained here. At the transmitting end, input data SI is processed through a pulse shaping function GT to get XT, which is multiplied with the spreading sequence SCT. Then the resultant is transmitted using a carrier frequency FC for modulation. The signal arriving at the receiving end, RT, is affected by multiplicative channel HT, additive noise NT, and additive interference IT. The signal is down converted prior to synchronization and despreading. The synchronization uses the baseband signal JT to align the delay tau of the receiver's spreading despreading code generator. The output after despreading exit passes through a match filter followed by a sampling at interval TS. So this is description of the previous block that we have already discussed. The sampled output, that is SI head, is then used for detection of the transmitted data. Now, the input to the match filter. So here, this block diagram, the signals at different points are expressed in the mathematical form. So here, X hat T is basically given by X hat T is XT is your transmitted information, which was multiplied by this spreading code, then was modulated. So at the transmitter, you had this information XT multiplied by spreading code, multiplied by cos 2 pi FCT, then transmitted over the channel. So that's why convolution with HT. Then at the receiver, you have the same spreading sequence is used. So over the channel, there might be delay. So shifted version of spreading sequence is multiplied here. Then you can have phase shift, or there might not be proper match between the when doing the demodulation. This shows drift in phase as compared to the signal which was used for modulation at the transmitter. So this is used for despreading. This is used for demodulation. Now at the receiver, noise is added, AWG noise, and interference is added. So these two components, since these two factors are coming at the receiver side, so these two factors will again will also be multiplied with noise as well as the interference component. So we have noise and interference component multiplied by despreading code, and for demodulation, this is coming from demodulation. Now here we are assuming that phi corresponds to phase error due to imperfect synchronization. If the transmitter and receiver are not perfectly synchronized, so in that case, we can use different value of phi, but if they are we are assuming that they are perfectly synchronized, so phi will be equivalent to 0. Now, receive signal under additive noise only for perfect synchronization in absence of multiple path and interference. That is, here we will be considering the effect of one parameter at a time. So here initially we are assuming that there are no multipath and interference. So in that case, no multipath, HT will be delta T, and in case of no interference, IT will be 0. The received signal will be given by this vector. So here X hat T is given by estimate of the signal. So you can rewrite this equation in different form. So this IT is 0, so this term will go off. Then HT is equivalent to delta T. So you can remove HT from here and the remaining things will stay. Now here we are assuming that for perfect synchronization, so if you are considering perfect synchronization, so delay will be 0 here. So here we will get SCT multiplied with each other. So you'll get SC square T. Then in case of perfect synchronization at the transmitter and receiver, you have cos 2 pi FCT square of this by multiplication of this and this. So you'll get this term. And then noise term will be written in this form. Now here we know that for spreading code sequence, PN sequence has certain properties. Using that, HC square T is equivalent to 1. We'll discuss different kind of coding sequence, PN sequences further in the lecture. So generally this assumption is made, or PN sequence are considered in such a way so that this is equivalent to 1. And if SCT is sufficiently wideband, so here SCT bandwidth of SCT is basically dependent on this terms TC, that is time period of the coding sequence, that is known as chip duration. So here if this is equals to 1 and if SCT is sufficiently wideband, then sufficiently wideband, that is you have length of PN sequence is sufficiently high, then in that case NT into SCT is 0 mean AWGN. So because in that case it SCT will turn out to be kind of impulses located at certain distances from each other. So NT SCT will be 0 mean AWGN with power spectral density N naught by 2. The match filter output over a simple time for GT is equivalent to, now if you consider in the same expression, at the receiver, the signal is passed through a match filter. So X hat T is then passed through a match filter matched to the transmitter. If you consider a square filter with characteristic given by GT is equivalent to root 2 by TS, with T time period, this T varies from 0 to TS. So at the receiver, if the signal is passed through match filter, then the estimate of transmitted information is given by this expression. G conjugate minus T represent your match filter for this pulse shape. So this is signal component and this is the corresponding noise component. The corresponding error probability. So using this expression, you can calculate the corresponding error probability for binary phase shift keying BPSK, which is given by PB is equivalent to Q root 2 ES by N naught, where ES is the bit energy. Here, we need to note that the spread spectrum signaling does not assist in error probability performance under AWGN channel. However, there is significant improvement in the performance in the presence. So here we observe that this bit or error probability expression is exactly same as that of the BPSK system. Now note that the spread spectrum signaling does not assist in error probability performance under AWGN channel. However, there is significant improvement. So we are not getting any advantage in terms of bit error probability performance, But here we are getting advantage in terms of improvement in due to multipath, because the same information in terms of diversity we are getting advantage here. In terms of BR performance, we are not getting any advantage because of spreading terms. So in the presence of multipath, and so here there is significant improvement in the performance in the presence of multipath and interference. So advantage in terms of these two parameters we are getting. Interference, because of despreading, a major portion of interference is removed. Also because of the spreading code, a major portion of interference is removed in the receive signal. Receive signal under additive noise and interference. Consider an example where IT is equivalent to I prime t cos of 2 pi fct is the interference signal at the frequency fc. Assume ht is equivalent to delta t. That is, here we are observing the effect of signal under additive noise and interference. Earlier we have considered only noise parameter. Here we are considering two parameters, that is interference and noise. So interference is basically given by I prime t cos of 2 pi fct is an interfering signal at frequency fc. Assuming here that ht is equivalent to delta t, that is multipath is absent here. Under perfect synchronization, the input to the match filter is given by, so here x hat t, that is the input to the match filter, is given by this expression. So again, spreading s square t, that is square of spreading code sequence, is equivalent to 1. So you get xt cos square 2 pi fct. Only additional term will be the interference term will be included here. So earlier we had only noise term, now we have interference term also. The corresponding demodulator output on passing through match filter will also have a interference component. The spread interference I prime t SCT is a wideband signal with bandwidth BC is equivalent to 1 by TC, when TC is the chip time. The integration over the spread signal acts as a low pass filter having bandwidth. So here the spread sequence, spread interference I prime SCT is a wideband signal with bandwidth. So here this is the bandwidth of the spread signal, that is inversely proportional to the chip duration, where TC is the chip time. The integration over the spread signal acts as a low pass filter. So here this integration basically acts as a low pass filter having bandwidth Bs is equivalent to 1 by Ts. So the bandwidth of this is a symbol duration. So here we are assuming, so here in CDMA system, basically BS is very small as compared to BC, because TC is very small as compared to TS. So that's why symbol bandwidth is very small as compared to the chip bandwidth. The most of the interfering power is removed. So here, since we are doing the despreading, so the portion which is there over the bandwidth other than the signaling bandwidth is automatically removed when you filter out the signal at the receive side. So here, because we are using PN sequence on despreading, the desired signal will only be concentrated in the bandwidth BS. So the portion which is there in bandwidth other than BS, since BC is very large as compared to BS, so the portion that is there in other portion other than BS will be automatically removed when you pass the signal through a filter. So this gives advantage in terms of automatically removing the interference component, and therefore improves the performance. Now receive signal under multipath and additive noise. Consider IT is equals to 0. That is, there is no interfering signal. So now we have considered the effect of additive noise. We have considered the effect of interference term alone. Now next is considering the effect of multipath. So consider we have instead of one path, that is direct path, we have two paths. So for considering the effect of multipath, since the analysis is complicated, so we are here assuming that IT is equals to 0. That is, we are not ignoring the effect of interference. We are only considering the effect of channel. That is, no interfering signal is there. Assuming a multipath channel with one delayed component. So the channel response is given by alpha naught delta t, plus, so channel has two components. So alpha naught delta t plus alpha 1 delta of t minus tau 1, where these two components are separated by a distance of tau 1, where tau 1 is relative delay in the arrival of the second multipath. Now here we are assuming that alpha naught is greater than alpha 1, that is the first receive component is stronger than the second receive component. Under perfect synchronization, the input to the match filter is given by, so now multiplying, so again the previous expression for x hat t, original one, will be modified in this form. So now we have two uh, uh, components from the desired signal. So alpha naught, alpha 1, here this term will be delayed by tau 1. So this is a distance tau 1. So here when there was no delay, you simply got s squared t, spreading sequence square t, and when there is a delay of tau 1 and the two spreading codes are multiplied, then this will be the resulting correlation between the two. Then you have also match filter that is used here at the receiver. So the components will also be delayed by tau 1 phase. Then AWG noise, and this is the component which is multiplied at the receiver side. So this is the estimate of the transmitted information at the receiver. X at t is given by this expression in case we consider the effect of multipath. Now, on passing this thing through a match filter, that is G conjugate minus T, we'll get this vector. Here we are considering same GT for all cases that was considered initially, that is root 2 by T. So the estimate of information is given by, so on detecting it, you have this is 1. So it is given by alpha naught Si, alpha 1, since this is the correlation between the two, S of L minus K, you have cos square, so you'll get this term from here. You have cos of 2 pi fc tau 1 on multiplication of these two and integration. Here again, you need to integrate this. So similar to the previous case. X hat t is integrated with G conjugate of minus T. G conjugate of minus T we have considered here to be dt is root 2 by Ts. So corresponding match filter is used here, which is the same as your GT in this specific case. So here on passing through this match filter, you'll get this as the estimate of transmitted information. Now here the correlation function, that is correlation of the two spreading sequence and its delayed version. It's rho c tau 1. If the spreading sequence is delayed by for matching is delayed by duration tau 1, so the correlation is given by this expression, and is the notation used is the autocorrelation of the spreading code at time t and delayed tau 1 over simple time. Now, if rho ct is equivalent to delta t, now in this specific case, if you consider that rho ct tau 1 is equivalent to or is equivalent to delta t, then the despreading process removes all ISI. So if this is delta t, then we will not have intersymbol or will not have this component, the corresponding to alpha 1. If this is delta t, then we will not get this component, and the received signal will be or the estimate of SI will only be the desired signal plus noise. So rho ct is equivalent to delta t, then the despreading process remove all ISI, hence the performance improves in terms of error probability. So if spreading sequence can be selected in such a way that you can get this relationship, then you have advantage in terms of automatic removal of ISI, intersymbol interference. But unfortunately, it's not possible to have finite length spreading codes with autocorrelation equal to delta function. So it's physically impossible to have a like uncorrelated sequence, like uh, it's like finite, since PN sequence are finite sequence, it's not possible to have n number of finite PN sequence which are completely uncorrelated to each other. So that's why you'll have some value of this parameter. Smaller the value of this vector, lesser is your ISI. There are various methods exist for designing spreading code with autocorrelation approximating delta function. So your objective here is to try to or determine the coding sequence or use the coding sequence such that your autocorrelation function tends to delta t. Now, these are certain properties of the spreading sequences. One is spreading codes are generated deterministically, often using a shift register with the feedback logic to create a binary code sequence of ones and zeros. So spreading codes are basically a sequence of ones and zeros, which are generated using a shift register with feedback logic in order to create a random sequence of ones and zeros, which are which has certain properties. So the shift register consisting of n stages. So based on your length of PN sequence, desired PN sequence, you have the shift register consisting of n stages. This shift register has n stages, has a cyclic output with a maximum period of 2 to the power m minus 1. Here this should be n. So so we know that if you have n stages in the shift register, then the maximum period, or maximum period in the sense that it repeats from it's a sequence of zeros and one. So like you have 2 to the power n minus 1 possibilities, because the other one of the possibilities will be all zeros. Other than that, you'll have 2 to the overall. If you have it's if your size size of the sequence is n, and the sequence can be ones and zeros only, the elements of the sequence can be ones and zeros only, then there are overall 2 to the power n possibilities. But since one of the possibilities is all zeros, so remaining or maximum period that you achieve is 2 to the power n minus 1. This is n here. Another thing that is required for the speed sequence is the balance property. So balance properties is that the code sequence are balanced so that each element of the sequence alphabet occurs with equal probability. So all the ones and zeros in this PN sequence occurs with equal probability. We require spreading code with autocorrelation. So the requirement for this PN sequence is that rho C tau is approximated by delta t to minimize ISI due to multipath. We require cross correlation among the sequences are small at all delays to minimize multi-axis interference. So here, one of the requirement is that cross correlation among the sequences. Since simultaneously multiple users will be communicating the data using different PN sequences, so the requirement is also that the cross correlation between the different PN sequences are small at all delays in order to minimize the multiple axis interference, so that we have smaller value of multiple axis interference. Now it is desirable for a number of consecutive ones or zeros called a run. So now another parameter for PN sequence that is desired is that in the PN sequence we know that it's constituted of ones and zeros. So at a time, the number of ones or zeros occurring in a sequence in continuation is defined as run. Should have some limited value. So it is desirable for the number of consecutive ones or zeros called a run to be small. So it is desired ones and zeros in this PN sequence should be as small as possible. If the count is large, if the run length is large, it reduces the bandwidth spreading and its advantages by a roughly a factor of k, right? So for a run of k consecutive ones or zeros, so bandwidth spreading reduces if the run length is relatively large. Now run length property, half of all runs are of length 1 and a quarter are of length 2. So here the PN sequence is designed in such a way that half of all the runs are of length 1. That is, most of the time, for 50% of the sequence, you have 1 followed by 0, followed by 1, and so on. So half of all the runs are of length 1. A quarter are of length 2. That means consecutive to 1 followed by 0, consecutive to 0 or 1. So that is, you have run length of 2 and so forth. So that a fraction 1 by 2 r of all runs are of length r for r finite. Now next is shift property. If sequences are shifted by non-zero numbers of elements, the resulting sequence will have half its element the same as in the original sequence and half its elements differ from the original sequence. So this PH sequence has this property also known as the shift property. So if sequences are shifted by any non-zero number of element, the resulting sequence will have half its element the same as in the original sequence and half its element different from the original sequence. So that is one of the property. Then a deterministic sequence that has the balanced run length and shift property as it grows asymptotically large, that is, so if the length of PN sequence is very large, large n is equivalent to the power m minus 1 is referred as PN sequence. So PN sequence generally is a large sequence. DSSS analysis is often done using random spreading sequences instead of deterministic spreading sequence owing to the former's analytical tractability. So here the spreading sequence should be deterministic, should be random instead of deterministic due to former's analytical tractability, so that the sequence is orthogonal. Among all linear code, spreading code generated from maximum length sequence or M sequence have many desirable properties. So this among all linear code, spreading code generated, this is M sequence is a kind of spreading sequence, has many desirable properties. So here M sequence are a type of cyclic code, thus are generated and characterized by a generator polynomial. So this is a kind of type of PN sequence, which is also used for transmission in CDMS system. So M sequence are a type of cyclic code, thus are generated and characterized by a generator polynomial. So a typical M sequence generator is basically a linear feedback shift resistor shown in the figure. The corresponding generator polynomial is given by this. So here, in order to obtain the PN sequence, we have generator polynomial which randomly generate different PN sequences. So here P1, P2, these are the factors. Here X represent shift to different shift resistor, and P1 are the corresponding multiplication factor, which are ones and zeros, and then we have addition of the corresponding factors. So here you'll get the output in terms of 0 and 1, which is then mapped to +1 and -1. So a typical M sequence generator is basically a linear feedback shift resistor that is shown here. The corresponding generator polynomial for this system is expressed by this expression. So here we have different factor polynomial multiplied, and then these represent different shift block shifted by 1 delay, 2 delay, and so on. And the output that is obtained in the form of a sequence will be used to as a PN sequence. Maximum length sequences are by definition the longest sequence that can be generated by an LFSR of a given length. For a shift resistor of length M, sequences of length this are generated. So PN sequences generated using this maximum length sequence are by definition the longest sequences that can be generated by LFSR of given length. For a shift register of length m, if shift register length is m, then sequences of length this can be generated, because last one 2 to the power m, one of the sequence will be all zeros. The m sequence have roughly the same numbers of zeros and ones over a period. So the generated PN sequence have roughly same number of zeros and ones over a, you can over a this duration, and 0 bits and 2 to the power m minus 1 bits, that is, it has a balanced property. We know that m sequence have roughly the same number of, so it will have these many numbers of 0 bit and these many number of 1 bits will be there also. So here we are verifying whether M sequences follow the property that are desired for PN sequence in a CDMS system. So the M sequence also they follow run length property, that is, you can you can have a specific number of ones and zeros in the sequence can be in continuation only. Then this M sequence, we'll check for shift and add property. The modulo to addition of M sequence and a time shift of itself result in a different M sequence corresponding to a different time shift of the original sequence. So we know that if you shift and add two PN sequence, it will generate another PN sequence. Since M sequence have the balanced run length and shift property of random sequence, they belong to the class of PN sequences. Next is autocorrelation. The autocorrelation rho CT of a M sequence code taken over a full period T is equals to NTC. Now we require that autocorrelation should approximate to delta value delta of T. So here we'll see what is the autocorrelation if we generate PN sequence or use M length sequences as a PN sequence, then what will be the autocorrelation. So it is given by rho C tau, and if you calculate for this, here period that is considered is NTC. TC is the chip duration, total time period or symbol period in the system is n time of TC and is given by this expression. Here rho C tau is equivalent to 1 minus. So these are the autocorrelation if tau is less than autocorrelation, and if delay, here tau represents the delay between the two PN sequence. If delay is less than the chip duration, then this will be the autocorrelation. If delay is greater than the chip duration, then the autocorrelation is given by factor minus 1 by n. Now this shows a plot of this autocorrelation function. So here at every value of so if this is greater than chip duration, then the correlation is minus 1 by n. So here that is represented using a graph here. So this states the autocorrelation of PN sequence. So we have peaks here at every TC duration. So if tau is not within a chip time of k and TC for any integer k, if tau is not within a chip time of n, k and tc for any integer k, then rho c is equivalent to minus 1 by n, which is equivalent to minus 1 by 2 to the power m minus 1. By making m sufficiently large, the impact of multipath component associated with delays that are not within a chip time of k and tc can be mostly removed. So you have ISI will be removed. Then we have limitation on M sequence. Although M sequence code have excellent property for ISI rejection, they have certain limitation which make them suboptimal for exploring the multi-user capability of spread spectrum. So the limitation of M sequence, so M sequence code have excellent property for ISI rejection. So we obtain the advantage in terms of ISI rejection. They have certain limitation which makes them suboptimal for exploiting the multi-user capability of spread spectrum. There are fewer codes of a given length n than in other codes, which limits the number of users which can share the total system bandwidth. So we can have a specific, we cannot go beyond a certain specific value of n. We can have limitation on the value of n, that is number of users that can be accommodated with the specified bandwidth, which limits the number of users who can share the total system bandwidth of multi-user DSSS system based on maximum linear codes. These codes have relatively poor cross-correlation properties. However, this end sequence has poor cross-correlation property. Hence, there are other methods also available which can be used for generating the PN sequence, like Gold-Casmi, Walls code are used instead of MLC because they have superior cross-correlation properties. Now, the synchronizer must align the timing of the so in the given, the synchronizer must align the timing of the spreading code generator in the receiver with the spreading code associated with one of the multipath component arriving over the channel. So this shows your synchronizer. At the receiver, you need to synchronize the spreading code to spreading code. The synchronization is achieved using a feedback control loop as shown below. So here we have the different sequences are matched using this correlator, and then so using this correlator, the different sequences are matched and then summed up, multiplied with the input sequence, and the output is observed. So this feedback control loop is used for synchronizer. The feedback loop adjusts the delay tau of the spreading code. So based on the outcome, it adjusts the feedback loop adjusts the delay tau of the spreading code generator until the function WT reaches its peak value. So here, until this parameter reaches, so this block works is iterated for multiple times until this WT attains its maximum value. Here, the tau is varied continuously in order to attain the maximum value of this W tau parameter. The feedback loop adjusts the delay tau of the spreading code until the WT reaches its peak value. At this point, under ideal conditions, the spreading code is synchronized to the input. An alternative to feedback control loop is parallel search acquisition system. This system has multiple branches that correlate the received signal against a delayed version of the spreading code. A similar structure is used in the rake receiver, which will be discussed next. So this alternative to this feedback control loop is parallel search acquisition system. The system has multiple branches that correlate the received signal. So this is one of the branches that is shown. Next, we'll discuss rake receiver, which has multiple branches and will be discussed next. So the rake receiver basically this is the receiver which is used for despreading the signal in a CDM system. So the rake receiver was invented in 1950s to deal with multipath on a spread spectrum. So here it exploits the advantage of multipath transmission in CDMA system. High frequency multipath of spread spectrum, high frequency transcontinental link. It is typically assumed that there is a multipath component at each integer multiple of chip time. So at every multiple of TC, you have a copy of the transmitted information that is assumed here. Thus, the time delay of the spreading code between the branches is, so here between time delay of spreading code is assumed to be TC here. The rake receiver is essentially another form of diversity combining. Since the spreading code induces a path diversity on the transmitted signal, so that the independent multipath components separated by more than a chip time can be resolved. Any of the diversity combining scheme, namely selection, so here shifted correlation is calculated for signals separated by chip duration, and then they are combined. So combining is done using either selection combining, equal gain combining, or maximum ratio combining. Either of the three combining scheme is used in order to exploit the advantage of diversity. MRC, however, gives the best performance. Here, each branch finger of ray correlates to a portion of the signal which is delayed by at least one chip in time from the other finger. So here, the different correlation in the rate receiver, correlation is calculated for duration or equivalent to TC, that is a chip duration. So each finger here is separated by duration equivalent to TC duration, one chip. So this is TC will be the minimum separation between the different fingers of the rate receiver. So here it is shown that this is the if received signal, here this is the spreading code sequence that is used, and then these are different delayed version of the same spreading sequence. Here received signal, we know that is demodulated at the receiver, so we are assuming that there is perfect synchronization here. So RT will be initially multiplied with cos 2 pi FCT for demodulation, and then is passed through, then despreading is done. In order to despread the signal, different delayed version of the spreading codes are used, and then these are then demodulated, and the corresponding estimate of the information are combined using maximum ratio combiner. So here you'll get the estimate will be based on a diversity combiner that is used here. So it basically exploits the multipath advantage of the system, as a different delayed version of the transmitted information are combined. So here, this can be mathematically modeled. Here is the example. If you can assume a multipath channel model with impulse response is given by this expression. So here we have HT is your multipath channel, where alpha G delta T minus JTC. Here, these are the separation. J fingers are used in the Maxwell. Sorry, here we are considering if the channel that affects the received signal is given by this expression. So, channel is J tap channel. Here, channel coefficients or this is your channel impulse response is given by this. Then here alpha G is the gain associated with the jth multipath, and J corresponds to the multipath with maximum delay. So here delta of T minus JTC will be basically the multipath with maximum delay, and for J is equals to 0, there will not be any delay. So that will be multipath corresponding to 0 delay. So larger J implies higher receiver complexity, but also increased diversity, because we are combining that many number of received signal at the receiver. So larger value of J will give you better because we are using combining scheme at the receiver. So more number of components of received signal or transmitted information are combined at the receiver if J is high. So you'll get the advantage in that form. However, it increases the complexity. The received signal RT correlates with the delayed version of the spreading code at each branch. So here we have seen that different version of the spreading code sequence are multiplied. So the received signal, so if there is perfect multiplication, or if the received signal is multiplied with the desired spreading sequence, then in that case that will give you your desired information. All other component constitutes your ISI. So the received signal RT correlates with the delayed version of spreading code at each branch. The output is coherently demodulated at each branch to get the statistic that is given by this expression. So in case desired PN sequence is multiplied, your square of PN sequence will give you 1 as the outcome. Otherwise, your correlation factor will be coming between the different PN sequences. Here, so this is signal power, and these two components will give you noise plus interference power, and this is the estimate of the information. So SI is the symbol transmitted over this as the symbol time. Here, this is symbol transmitted over symbol time. This. These are symbols other than the desired. These are a component of signal in direction of other PN sequences. Here, this is noise sample associated with the demodulator in the ith branch. If SIG is not constant, then ISI term is, if this term is not constant, then ISI becomes more complicated. However, in all cases, constant or non-constant SIJ, the ISI is reduced by roughly the autocorrelation, this factor. So under all circumstances, there will be a reduction in intersymbol interference. So because of the different PN sequence, this term, even if this will not be a perfect delta function or is not equals to 0 here, this because of PN sequence, it will have small value, and that ultimately will reduce the intersymbol interference. If rho c t is equals to 0 for tau greater than tc, then ISI term in each branch can be neglected, and the performance of the reg receiver with j branches is identical to any other j branch diversity technique. Spread spectrum is not usually used for diversity alone, as it requires significantly more bandwidth than other diversity techniques. If spread spectrum is used for its multi-user or interference rejection capability, then RAKE provides a simple mechanism to obtain the diversity bandwidth. So for detection, it exploits the diversity advantage as well as provides the interference rejection advantage. Spread spectrum can also be used as a mechanism whereby many users can share the same spectrum. Accommodation of multiple users in the same spread bandwidth is called spread spectrum multiple access, which is a special case of CDMA. So these are certain, we'll be discussing spread spectrum. We have discussed that is of two types. One is direct sequence and one is frequency hop. We'll be basically discussing direct sequence. So direct sequence spread spectrum can also be used as a mechanism whereby many users can share the same spectrum. So here we repeat, the same spectrum is used and will be shared by, that is standard property of any spread spectrum irrespective of FHSS or direct sequence. Then we have accommodation of multiple users in the same spread bandwidth is called spread spectrum multiple access, which is a special case of CDMA. Here, each user is assigned a unique code which is used to modulate it. So we are discussing, we have generated the PN sequence. We will be discussing its use with respect to DSSS, multiple user, when multiple users are transmitting simultaneously. Here, each user is assigned a unique code which is used to modulate its data signal. Now, next is the transmitted signal for all users are superimposed in time and in frequency. Now, since all PN sequences are different for each user, so simultaneously all the users can transmit, and for detection, the receiver should have the desired PN sequence in order to decode its information. So since these PN sequences are independent, or you can say are orthogonal to, almost orthogonal to each other, you can transmit all information simultaneously over the channel. Then performance of multi-user spread spectrum, it depends upon these parameters, whether spreading code are orthogonal or non-orthogonal. So this is one of the factors in order to determine the performance. When codes are orthogonal, then users do not interfere with each other under ideal propagation condition. Otherwise, the user interferes with each other. So that is one factor here. The other factor is whether the multi-user system is a downlink or an uplink transmission. So whether we are using CDMA system for downlink or uplink transmission, that is also a factor. In downlink, the transmitted signals are synchronous as they originate from the same transmitter, whereas in uplink, the users are typically asynchronous as they originate from different sources. In uplink system, we have downlink is basically base station to multiple users. Uplink is multiple users which are located at different location will be communicating with the base station. So here, when base station is transmitting, it's easier to synchronize. PN sequence can be synchronized, but if multiple users are transmitting, which are located in different location, so synchronization will be a bigger issue. So next, spreading codes for multi-user DSSS. M-sequence code have poor cross-correlation properties, hence are not desirable. So we have considered that M-sequences can be used as PN sequence for transmission in DSSS, but M sequence have poor. We have observed that the cross correlation was plotted for M sequence, and it was observed that they have poor cross correlation property, hence are not desirable in multi-user DSSS system. A higher cross correlation among spreading code result in higher multiple access interference. Multi-user DSS, so it generally does not use this scheme. Instead, it uses other scheme, that is Gold-Kasmi Walsh-Hedmert code, which has superior cross-correlation properties. Although these codes can be less effective at ISI resection than M-sequence code. So these codes will have lesser advantage in terms of ISI resection. The cross correlation of code assigned to asynchronous user I and j over one symbol time with relative delay tau between the user. So if there is a delay between, or if the users are asynchronous, in that case, the cross correlation between the two PN sequence is computed in this way. So here, if this is the overall symbol period, these are the two spreading code, and this is spreading code, delayed spreading code integrated over the symbol period. It can be rewritten in this form. Since we are sampling at every TC chip duration, or so here you have m is equals to 1 to n. So it can be, for discrete system, it can be written in discrete form, it can be written in this form. For synchronous user, signal arriving at the receiver are aligned in time, so tau is equals to 0, and cross correlation can be written in this form. So if they are aligned, tau is equals to 0, and you can rewrite this expression in this form. So this holds for asynchronous system, this holds for synchronous system. Here we are considering that the symbol duration is divided into n fragments, and then we are summing that up. Then we have orthogonal chord set. The spreading code have rho ij is equivalent to 0 for all tau for asynchronous user, and for rho ij is equals to 0 for synchronous users, form orthogonal chord set. So here, in order to achieve, in order to have the desired property for PN sequence, we need to have this equivalent to 0 for both synchronous and asynchronous system. That is this to be 0 and this to be 0 for asynchronous in this case and synchronous in this case. So the spreading codes have rho ij is equals to 0 for all tau for asynchronous user, and this is equals to 0 for synchronous user, from orthogonal chord set. Then Gold and Kasmi codes are non-orthogonal and are derived from n sequence, which can be used. Kasmi code have better cross correlation property than Gold code. Then we have Walsh-Hedemeier code. Walsh-Hedemeier code of length n, TS by TC are synchronized in time and are orthogonal over a symbol time TS. So these are the property of Walsh-Hedemeier code. They are of length n, and here n is equals to symbol duration divided by chip duration Tc are synchronized in time and are orthogonal over a symbol time Ts. These codes are useful in downlink but rarely used in uplink due to challenges occurring in synchronizing the users. Walsh-Hedman chords of length n are obtained from rows of an n cross n Hedman matrix. This Hedman matrix is given in this form. For n is equals to 2, if n is equivalent to 2, then in that case, the matrix is given by this. Larger Hedman matrix are obtained using H2 and the recursion. So this matrix can be repeated in order to obtain the large Walsh-Hedman matrix. So the example is given. So here matrix of dimension 2 is this of 2n where n can be any value. Here n is this matrix is repeated and we obtain h of 8. Now this is how the downlink and we can have downlink or uplink transmission in a CDMA system. So downlink is from base station to the user equipment. So in case of downlink transmission, each user information is multiplied with the spreading code sequence and is summed up and communicated over the medium, which is represented using this diagram. And at the receiver, the same spreading code need to be multiplied in order for this information to be detected at the specific user. So this summed information is communicated over the channel. So some information is transmitted and then is for transmission it is modulated by multiplying with the carrier, and ST is the signal which is propagated over the medium. This is the receiver diagram for downlink system. So here receive signal ST is multiplied by, so this is not the so ST is the communicated signal. Now when you transmit ST over the channel, then ST will be multiplied by the attenuation or factors affecting the channel. Then there will be additive AWG noise. In case interference is there, then that will also be added here. These are the effects of the channel, and this indicates your receiver. So at the receiver, you demodulate the signal, multiply it with the corresponding carrier, pass it through a match filter and estimate the information. So this is a block diagram of downlink receiver. Here the spreading sequence are specific to each user and are known to the specific user, which can easily detect the transmitted information. However, when you so for k user system, the transmitter sends to k independent user the baseband modulated. So this block diagram, the corresponding mathematical representation of this is given by this. So the combined signal for k user system, the transmitter sends k independent user. So simultaneously, transmitter communicate the information to k users. The baseband modulated signal associated with the kth user is given by this expression. Here, GT minus ITS basically indicate your pulse shape. This is the information. This is the cumulative signal, which is then passed through PN multiplied with PN sequence and communicated over the channel. This is information. This is pulse shaped. So this is pulse shaped and summed information, which is then passed through PN sequence and then is modulated. The signal is then modulated and then this is communicated over the channel. So here it's expressed in mathematical form. The k branches are summed together resulting in baseband. So if you have k number of users are there, so in that case, information for each user, so XKT represents information corresponding to kth user is multiplied with spreading sequence corresponding to kth user, and then this indicate your combined signal ZT, that is the signal here, and then this ZT is modulated and is communicated over the channel. So this multi-user signal is multiplied by the carrier to obtain the passband signal ST, which is transmitted over the channel. Now at the receiver, the received signal at kth user is given by RKT, is the received signal at kth user, where HKT indicates if the channel state ST is your receive signal. ST is your signal communicated over the channel. ST and then is convolved with HKT. If you have multipath, then you can have different values of K parameter based on number of multiple multipaths are there. The received signal at the kth user receiver is given by RKT is equivalent to HKT ST. So this is received signal, that is convolved with transmitted information, convolved with channel and the noise. This received signal is down converted, despread using SCKT and then processed through the mesh filter. The demodulator output associated with the kth user over the kth symbol time. So this is the estimate of the demodulator. So this is information received at the receiver, then passed through correlator, demodulated, then so this is the correlation that is calculated. So this gives you estimate of the transmitted information. For HKT, if channel is um, uh, given by alpha k delta t, that is one path is there. So in that case, estimate of information is given by, so here we are considering you have each link is single path. So you have k number of users are there. Each user information is affected. So this is the channel for each user. So here we are considering k users are simultaneously the receive signal at kth user. So this is receive signal at kth user. So this indicates channel from source to the kth user, and this is the cumulative signal convolved with channel connecting source and the kth user. Since these users are located at different location, and NKT basically represent noise added at the kth user. The demodular modulator output associated with the kth user over the LH symbol time is given by, estimate is given by this expression. So this is the communicated information at the receiver. Despreading is done, then matching with demodulation is done, and then if channel is given by this uh, channel from source to kth user is given by this expression, then it can be written in this form. Now the estimate of the information at the kth channel, which has a which need to have a specific PN sequence. So if you use the corresponding PN sequence, you will get this as the desired signal, and all the other displacement of the uh, all other will give you the mutual excess interference, and then you'll get the noise component. Not that the desired interference part experience the same fading alpha k, since here we observe that the spectral alpha k is common among both desired signal and the interference term. It is because both follow the same path from transmitter to the receiver, because interference is basically, here we have, so here we have this term multiplied by this. So you'll get multiple shifted version of correlator, and you'll get this is represent your interference here. Now next is, if your interference limited for interference limited scenario, interference dominates over the noise. The signal to interference ratio for a synchronous k user system with k n chips per symbol is given by. So signal to interference ratio in this case is given by n divided by k minus 1. Here n is related to G, which is related to basically TC, that is your chip duration. K minus 1 is the number of interfering users, all the other users other than the desired user. Here you observe one term is there. All other K users, K minus 1 users will act as an interference for the desired user. So this basically denotes the interference coming from a user other than the desired user. So that will come in the denominator. Since we have K minus 1 undesired users, so interference component will have factor K minus 1, and N is coming from the, since we have n chips per symbol, so that's why n is there in the numerator here. So gain, n is related to G. So where G is approximated as n is the processing gain. If the noise component is comparable with the interference component, so if you have here we are ignoring we are only considering signal to interference ratio. If you are considering this noise term also, that is signal to interference and noise ratio. So in that case, this expression will be modified in this way. If noise component is comparable with the interference component, that is noise and if noise is very small as compared to interference, you can ignore it and you can write it in this form. If noise component is comparable to the interference component, then SIR ratio will be modified in this way. You cannot ignore the noise component. Here, this is an uplink system. Uplink system is when multiple users are transmitting from different location to the basement, to the base station. So here you have here multiple user, each having its own spreading sequence, which are located at different location and are using different modulator for modulating the information. You can observe here. So this modulator has reference phase as phi1, this modulator has reference phase as phi k, and so on. So these are the different spreading information which are communicated, spreaded information which are communicated over the channel. H1T and HKT, again for k different users, you have k different paths. The signal at the receiver is summed up and passed. So here you have at the receiver base station, it will be received. So the combined signal will be received, and this is represent your additive noise at the receiver. So RT will be your cumulative signal. This indicates your uplink receiver. So at the uplink receiver, how you do the demodulation. So on the same system, multiple signals will be detected. So at the receiver, you have these basically indicates your demodulator. So we have seen that we had different phases can be different for each demodulator, since all users are located at different location and there is no means they can communicate to each other. So this represent your phase corresponding to the specific user communicating the information. So then we have this multiplied with the spreading, this is de-spreading the signal, then pass through match filter, and then sampling and estimate of the signal is done here. So the transmitters are typically not synchronized since they are not co-located. All key users transmit the passment signal SKT over the channel HKT. The corresponding uplink receive signal will be given by this expression here. So the corresponding uplink receive signal, so that is at receive signal will be XKT is transmitted information this is correlator, this is phase demodulator at the receiver, this is channel information plus additive noise. Since all the K users are transmitting simultaneously to the same base station, so signal from all the users are combined at the base station and then will be detected. So 5K is the here 5K is the carrier phase offset between the this thing demodulator block. If the receiver signal is down converted, despreaded using this and then processed through the mash filter. So this will be the corresponding receive signal at the receiver in case of uplink transmission. So the demodulator output associated with K user over the LS symbol time. So this is the estimate of this signal. Here we have, this basically indicates so this is the estimate of the signal. So estimate is basically you pass the signal through a mash filter. The receive signal is multiplied with this and this block and is passed through a mash filter. So on passing through the mash filter, here this represents your mash filter here. You'll get the estimate of the transmitted information. Here 5K is the phase offset obtained by carrier recovery loop in the kth branch, and this is the in-phase component of the equivalent low pass filter for HJ. For HJ low pass, the demodulator output for the kth branch over the LH symbol time is, so here if we consider that HJ T is given by this expression, then the demodulator output for kth branch over the LH symbol time is given by this expression. So you'll have one desired component and other components will be undesired. Here, because of mismatch in the phases between the at the transmitter and the receiver, this component will come as interference here. Then this represent due to different spreading sequence, you have correlation factor here. This is your undesired signal. These are the coefficients due to channel, and this indicate your interference noise. So here this represent your phase difference between the correlator or between the this thing modulator and demodulator at the transmitter and receiver. Then again here we calculate this indicates your signal power, this indicates your interference power, and this your noise power. So using this you can write the expression for SIR and SINR. So SINR is given by this expression, that is signal power divided by interference power and the noise power. So you'll get this expression. If you consider signal to interference ratio only, so in that case, the signal to interference ratio, you have K minus 1 interferer, multiple excess interference simultaneously. So K minus 1 term in the denominator, and then you have Cn in the numerator. So the kth user symbol and multi-user interference are attenuated by different channel gains. If alpha G is greater than alpha K, the uplink suffers an SIR, SINR penalty due to different channel gains. So here, if the difference is large, the uplinks between alpha J and alpha K, that is a channel attenuating different links meant for different users, then penalty due to different channel gains will be there, and it is known as near far effect. Since user far from uplink, receiver will generally have much smaller gains to the receiver than those to the of the interference. Methods of power control can be utilized to tackle near far problem. Then here represent how the power control can be done. Power control is basically based on channel inversion. That is a solution to near far effect in DSSS system, uplink systems. The kth user transmits signal power P is P by alpha k square so that its received signal power is P regardless of path loss. The disadvantage of channel inversion is that it can require very large transmit power in some fading channel. Moreover, channel inversion can cause significant interference to other operating user at the same frequency. Then the channel inversion based power control is used in IS-95 cellular system, ISI cellular system standard. So these are the, in order to tackle near fire problem, you can do the power control that is mentioned here using the different methods. Okay, thank you. With this, I'll conclude the lecture. If you have any questions, you can ask the same. If you have any questions, you can ask.
Participants, if you're having any questions or queries, please put in the Q&A section. Ma'am, there is one question from participants who is asking, like, is this technique the same in satellite communications?
This is standard CDMA system. So like wherever CDMA is used, it's the method is common. For CDMA transmission, this is used. So wherever the standard is followed, so this spreading and despreading, CDMA basically here we are discussing about spreading and despreading method. So wherever CDMA is used, this is applicable.
Yeah, thank you, ma'am. Like, he's saying that he's asking this question with respect to spread spectrum.
So spread spectrum is what? Spread spectrum is spreading the sequence and then despreading it. So like wherever spreading and despreading, direct sequence spreading is done, then we mainly discuss direct sequence spread spectrum. So wherever we are spreading and despreading is done, we use the PN sequence and the same things will hold. It's basically like it discuss how spreading and despreading is done and how the signal is combined.
Thank you, ma'am. Any more queries from the participants?
However, in long distance communication, it will be like in satellite communication is basically a long distance communication. So the power that is there may not be feasible for long since when we are spreading the signal, so signal strength reduces to a very small value. The signal which is communicated over the channel will have very small power, which may not be applicable for satellite communication. So like the CDMA system is generally used in communication system, but the relative distance between transmitter and receiver is not very huge. Any other question?
No, ma'am. No questions yet.
Okay, thank you.
Yeah, thank you, ma'am. Thank you for the informative session.
Thank you.
And participants, so we'll be ending the meeting here. for today's session here. So in case if you have missed out any portion of this session, you may please visit the YouTube link that is given in the drive. So please, and it's a request to all of you to please keep checking the drive link, because all the important announcements and updates are given over there. So sometimes even if you miss out some announcement in this platform, you can visit the drive and get yourself updated. So we are so today's session is over, and from tomorrow onwards also a request, like many of you are still not joining with your registered email ID, so that becomes very difficult for us to track your attendance. So please try to register with your registered email ID only. Thank you. Thank you, Kalpana ma'am. Thank you, coordinators, all the participants. So we are ending the meeting for today. So please get connected tomorrow by 9:30 a.m. Thank you.
Thank you.
Thank you. Thank you, sir.